So let's now start our revision on telescopes. So the first question says a magnifying glass has a focal length of 15 centimeters. It is held 5 centimeters away from a component which is being examined. Determine the magnification of the images. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you've got to remember that if it's got a focal length of 15 centimeters, we can say f is 15 centimeters. It's held 5 centimeters away from the components being examined, so u is 5 centimeters. We've then got to use our equations for lenses, which is 1 over f equals 1 over u plus 1 over v. Pop in all the values, and you get v to be minus 7.5 centimeters. Now, we also know magnification is going to be v, which is the image length divided by u, the object length. So it's 7.5 over 5, so it's the magnification of 1.5. The next question say the James Lick telescope at the Lick Observatory in California, USA was built in 1888 and is still in use. It has a primary convex lens of 36 inches and a focal length of 57.8 feet. What is this magnification if used with the eyepiece of focal length 55 millimeters? What is the sum of the focal lengths FO and FE, and how would you calculate change for an eyepiece of focal length 35 millimeters? Calculate the angular magnification of a telescope with an objective lens of focal length 1200 millimeters using an eyepiece of focal length 25 millimeters and 10 millimeters. Then the moon has an angular size of 0.5 degrees in the sky when viewed with the naked eye. Suppose the moon is viewed through a telescope with an objective focal length of 100 centimeters and an eyepiece of focal length 200 millimeters. What is the angular size of the moon as seen through this telescope? And the 1 meter diameter objective lens of the Yerke refractor weighs 225 kilograms. Suggest two factors that limit the size of refractors for astronomy. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know in the first case, FE is going to be 55 millimeters. So magnification we know is FO over FE. That's an equation you've got to learn. Pop in all the values, so our magnification is 320. Now we also know that FO plus FE is going to be 17.6 meters, which should be the entire length of that telescope. Now again, for the second one, FE is 35 millimeters. Pop in the values for magnification, and therefore we get 503. And again, the total of the two added up again is about 17.6 meters. Now in this next one, like we said before, magnification is going to be the objective focal length divided by the eyepiece focal length. So it's 1200 as given, divided by 25. You don't need to convert millimeters into meters because it's a ratio, so we get 48, whilst for the second one it's 120. Now we also know here that we can work out the angular size, because we can say magnification is going to be the angular size of A over the angular size of B. So in this case, the moon has an angular size of 0.5. We've got our objective focal length and our eyepiece focal length, so we can equate them and say angular size of A over the angular size of B is equal to FO over FE. You pop in all the values, you work it through, and it's 25 degrees. Now in the next question here, okay, what's the two factors here? Well, one factor is that refractors with a high magnification will have large objective lenses, which makes them very long. So we need to have giant domes to house them. And another factor is that you've got to make large glass lenses that are so heavy that the gravity causes them to sag under their own weight, because you can't support it in the middle because it will block out the light refracting through. So therefore it distorts their shape, and therefore the image that is formed will also be distorted. The next question say a telescope is used to observe distant galaxies. It has an FO of 0.52 meters and an FE of 0.0010 meters. Calculate the magnification of the telescope. The image of a distant galaxy by a telescope subtends an angle of 0.331 radians at the eye. Calculate the angle subtended by the galaxy at the unaided eye. Then what assumptions can be made about light rays reaching the Earth from a distant object in space? What type of image is formed through an eyepiece lens of an astronomical telescope, and then give an equation for the magnification of an astronomical refracting telescope in terms of the focal lengths of the lenses, and then finally explain why astronomical refracting telescopes have to be very long to produce a highly magnified image. So pause the video now, then unpause the video when you want to go through your answer. So, in this first question, how to work out the answer? Well, the magnification, as we talked about before, is going to be FO over FE. So you're keeping the same units to get the ratio out to be 520, the magnification. Now, again, our other way to work out angular magnification is the angle of the angle subtended by the image divided by the angle subtended of the object. Rearrange it to get into the angle subtended by the object. Pop in all the values through. Remember, the magnification of the telescope will be constant in this instance if the lengths don't change. So therefore, it's 6.365 times 10 to the minus 4 radians. Now, our assumption about light rays reaching the Earth from a distant object in space is that they've travelled so long that the light rays are now parallel to each other. Now, you should know this is a fact. The image formed through an eyepiece lens of an astronomical refracting telescope should be a magnified, upright, and virtual image formed in the eyepiece lens. Now, again, the equation that allows you to find the magnification for an astronomical refracting telescope is FO over FE, and we know that because that's the equation for magnification, an astronomical telescope needs to have a large FO to get a large magnification. So if that focal length is very long, therefore the telescope will be very long. The next question says, what are the advantages and disadvantages of a refracting telescope? So pause the video now, then unpause the video when you want to go through your answer. Right, in this one, the advantages are that refractors require less maintenance than reflectors, and refractors are also not as sensitive to temperature changes as reflectors can be. But the disadvantages of a refractor tend to be 5 key issues. It's the size. Firstly, it's difficult to make large diameter glass lenses which are completely free from defects when you need them to refract. Now, a larger magnification requires larger objective lenses, so therefore very long focal lengths. Your telescopes are very, very long in construction. The second issue is the weight. So large diameter lenses are very heavy and tend to distort under their own weight, especially because we can't support them behind them. So therefore the refractors are also very heavy and then difficult to move into position, so can't respond to astronomical events as quickly. In terms of construction, the lenses can only be mounted and supported around their edges, as we mentioned before, but that's actually where they're the thinnest and the weakest, so that is also an issue. The image quality will suffer because refractors will have both issues with both chromatic aberration and spherical aberration, and again the ability to observe non-visible wavelengths is difficult because refractors will only be able to observe wavelengths of visible light. Now the next question says, what are the advantages and disadvantages of reflecting telescopes? So pause the video now, then unpause the video when you want to go through your answer. Right, in this next question, we can link it through to the different parts of the reflecting telescope. So the advantages are, firstly, that their size. The diameter of a mirror can be much larger than that of a lens, so the greater magnifications can be achieved. The arrangement of the mirrors will also allow reflectors to be much shorter in length than refractors, because several small mirrors can be used to form one large composite mirror. Secondly, the weight. Now, the large single mirrors can be made which are more light and easily supportable from behind, because you don't need to worry about blocking out light passing through the mirror. So refractors tend to be lighter, which allows me more rapid responses for astronomical events. In terms of constructions, mirrors only use the front surface for reflection, which eliminates many of the issues that you get when you've got a lens which has has 2 surfaces, but also goes through the particular glass as well. So therefore it means the mirror surface can be made very thin, which allows for a greater image detail. Now, mirrors cannot produce chromatic aberration, but they will suffer from spherical aberration, but only if non-parabolic mirrors are used. And again, reflectors can be designed to observe wavelengths of light from outside the visible spectrum, so reflectors can be sent into space, which also eliminates light absorption due to the atmosphere. Now, the disadvantages of a reflector are that the secondary mirror will block out some of the light from entering the primary mirror, so you'll lose some of the information from your source. The secondary mirror and its support will also cause some diffraction as the waves pass along the secondary mirror, which will affect the clarity of the image. The mirrors in reflecting telescopes are also exposed to the air, so will require regular maintenance, and that'll cost more money. And then finally, light is refracted in the eyepiece lens, so you will get some chromatic aberration at the stage of refracted into an image to be observed by a human. The next question says, a reflecting telescope with a parabolic mirror has a diameter of 80 centimeters and a focal length of 1 meter. It is used with an eyepiece of 15 millimeters. What is the magnification of the telescope? Then what is the magnification of a Cassegrain reflecting telescope whose mirror has a focal length of 2,800 millimeters and is used with eyepieces of focal length 5 millimeters, 15 millimeters and 25 millimeters? So pause the video now, then unpause the video when you want to go through your answer. So for this first question, how can you work out the magnification? Well, as we said before, magnification is FO over FE, so we've got to keep it in the same unit, so it's 1 over 15 times 10 to the minus 3, so it's 67. In this next one, we're doing the same unit, so we're fine, so it's 2,800 over 5, 560. Next one, 2,800 over 15, 187. And then finally, 2,800 over 25, which is 112. The next question says, what is the resolving power of a telescope? What sort of pattern is produced when light passes through a circular aperture? What is the central part of this pattern called? What effect does this have on the resolution of the telescope? What is the Rayleigh criterion? Give 3 examples of problems when using refracting telescopes, and give 2 advantages of using reflecting telescopes compared to refracting telescopes, assuming they have the same magnification and the resolution power. So pause the video now, then unpause the video when you want to go through your answer. Right, the definition of resolving power, you've got to learn it, is how much detail a telescope can see. Now, when you pass through a circular aperture, the light will diffract and produce a diffracting pattern. Now, the central circle of this pattern, which will be a circular shape, is called the airy disk. Now, a telescope is defined to have a poor resolution if the airy disk of light that makes up the image overlaps with that first maxima of your image being produced. So the Rayleigh criterion in an equation is theta is equal to lambda over d. Now, the issues with refracting telescopes are you'll get chromatic aberration, bubbles and impurities in the lens which will absorb or scatter radiation, so you won't get a very clear image. Building lenses of good quality is expensive and difficult. Large lenses are heavy and can sag, and for a large magnification a refracting telescope needs to be very long and it can be difficult to house. Now, the advantages of reflecting telescopes are it's easier to make good quality mirrors. Mirrors do not suffer from chromatic aberration. It's cheaper to make larger mirrors than lenses. Lenses can be supported from underneath, so are less likely to sag as well. The next question says, the supermassive black hole at the centre of the Milky Way galaxy is 25,000 light years from the Earth. It has a Schwarzschild radius of 1.2 times 10 to the 10 metres and emits radio waves at a frequency of 230 GHz. The Event Horizon Telescope is an array of radio telescopes which has the same resolution as a single radio telescope with a diameter of 8,000 kilometres. Calculate the minimum angular separation, which could be resolved by the EHT, then deduce whether the resolution of the EHT is suitable to obtain a detailed view of the supermassive black hole. Support your answer with a calculation. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, what can we say? So, the minimum angular separation is going to be linked to the wavelength. So we can say lambda is equal to c over f. So you can pop that all through. Remember, f is going to be linked into what you've got here. So you've got 230 times 10 to the 9 there. So you can work that all through. So you get, and then when you work out your wavelength, you can then link that into your angles by then turning it into that by times by 8,000 times 10 to the 3. So therefore you would get 1.63 times 10 to the minus 10 radians. So this means that the EHT can obtain a detailed view of objects down to the angular size of 1.63 times 10 to the minus 10 radians. So that will then allow you to work out your minimum angular resolution. We also know that theta is equal to S over D. That's an equation which you've covered before in mathematics. So you can say theta, the angle, is equal to S, the distance, over D, as so. So you can pop in all your values, you work it through, and you get 1.01 times 10 to the minus 10 radians. So we can see here that the value of the minimum angular separation provided by the telescope is greater than the angle subtended by the actual supermassive black hole. So that's about 1.6 times greater than the limit, so therefore it wouldn't be able to resolve a detailed image of the black hole. So the angle of the black hole can be, as viewed from the Earth, is wider than the angle that the telescope can view. The next question says, the largest refracting telescope still in operations is the Yerkes refractor. The construction of this telescope later paved the way for the Otto Struve reflector to be built. Both telescopes detect optical wavelengths of light. So the table below summarizes some of the properties of the two optical telescopes. Now compare the two telescopes in terms of their collecting power and resolving power. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? Well, collecting power, we should be able to understand that collecting power is proportional to the area, which is proportional to the diameter of the telescope squared. So you can see that the ratio of the two collecting powers is going to be the ratio of the two diameters of the telescope squared. So you do 208 over 102, square it, so you get about 4. So that tells you that the Otto Struve reflector is about 4 times greater than the Yerkes refractor, meaning it will produce brighter images. Now, for our resolving resolving power, or the minimum angular resolution, is proportional to 1 over d, because theta equals lambda over d, the Rayleigh criterion. Now you don't need to consider lambda here, the wavelength, because we'll just say it's the same wavelength of both. So you can do the ratio of the two of them. So you do 102 over 208, so it's 0.5. So that tells you that the Yerkes refractor can resolve detail half as well as the Otto Struve reflector. So it means that the resolving power of the Otto Struve reflector is twice as great as the Yerkes refractor. So not only will it produce brighter images, it'll also produce clearer images as well. It's very important to link those conclusions into your answer. The next question says, compare and contrast a radio telescope with an optical telescope. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, what do we know? That for an optical telescope, they're similar because they both use parabolic surfaces to reflect waves, but the differences are a radio uses a single primary reflector whilst the optical uses two different mirrors, and a radio dish does not need to be as smooth as an optical mirror. In terms of positioning, both are ground-based as the atmosphere is transparent to both radio and visible light waves, but the differences are that the optical has to be placed higher up to avoid atmospheric distortions and also away from cities to avoid light pollutions, whilst our radio telescopes must be located remotely away from populations, so will be away from radio sources. Now both of the telescopes are used to detect hydrogen emission lines, but radio waves are not absorbed by dust, but optical waves are, so therefore radio telescopes are used to map the Milky Way where there's lots of dust. Now, in terms of linking this through, we can say that for resolving power, radio waves are longer than optical waves, so the radio telescopes have a much lower resolving power than optical telescopes, and optical telescopes are more likely to produce detailed images. Now, in terms of collecting powers, radio telescopes are larger in diameter, so have a greater collecting power than optical telescopes, so therefore it's more likely that radio telescopes will produce brighter images, but many radio sources in the night sky are very weak. The next question says, compare and contrast an infrared telescope with an optical telescope. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this one, what's looking like for our optical and our infrared? So in terms of similarities, both infrared and optical use primary concave mirrors and a secondary convex mirror. The differences are, though, the mirrors in an infrared telescope must be kept very cool to avoid interference from the telescope itself producing infrared radiation. In terms of positioning, many ground-based telescopes can detect both optical and near-infrared as long as they're positioned away from cities and are high above the ground. That's because infrared radiation is strongly absorbed by water vapor in the atmosphere, so telescopes must be built in a very dry, high altitude location such as a desert or above the atmosphere in the mountains. Now the atmosphere is transparent to most optical wavelengths but does block a lot of infrared wavelengths, so space-based infrared telescopes are preferable to Earth-based ones. And in terms of uses, most objects emit visible light and infrared radiation, so you can get information on an object from both these types of telescopes. Now, infrared telescopes can detect warm objects that don't emit visible light, such as dust in nebulae which has been heated up, or also brown dwarfs. Now, in terms of the resolving power and the collecting power, infrared telescopes have a lower resolving power than optical telescopes of the same size because from the Rayleigh criterion they have a longer wavelength. But the collecting power of infrared and optical telescopes will be similar because their diameters of the dishes are similar in size. Now the next question says, compare and contrast an ultraviolet telescope with an optical telescope. So pause the video now, then unpause the video when you want to go through your answer. Right, in this one, what's our similarities? Well, in terms of structures, both UV and optical telescopes have a primary concave mirror and a secondary convex mirror. In terms of differences, mirrors in the UV must be much smoother than those of optical telescopes because of the wavelength of UV. In terms of positioning, many space-based telescopes can detect both optical and UV wavelengths. Now, all UV wavelengths are strongly absorbed by the atmosphere in the ozone layer, so UV telescopes must be located in the upper atmosphere or in space. So therefore space-based UV telescopes can be inconvenient to maintain and are a lot more expensive. Now in terms of uses, both can be used to detect the chemical compositions and temperatures of objects, and many objects that emit visible light will also emit ultraviolet radiation, so you can get information on the object from both telescopes. Now UV telescopes can detect objects not visible at other wavelengths, such as very hot gas clouds near stars, supernovae explosions and quasars. In terms of comparisons for resolving power and collecting power, UV telescopes have a much higher resolving power than optical telescopes of the same size because of the Rayleigh criterion, they have a shorter wavelength. In terms of collecting power, again, they're very similar to each other because the diameter of their dishes are very similar. The next question says, compare and contrast a gamma ray or X-ray telescope with an optical telescope. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, what can we say? Well, the structure of X-rays and optical telescopes are similar because they both use parabolic mirrors to reflect and focus waves. Now, X-ray telescopes are made from a combination of parabolic and hyperbolic mirrors, which are going to be very smooth because of the low wavelength of an X-ray or gamma ray. And gamma ray telescopes don't use mirrors at all, but they'll use specialized detectors and grazing mirrors to ensure that the telescope works. In terms of position, an X-ray, gamma ray and optical will all perform best when positioned in space or away from anything to do with the Earth's atmosphere, because all X-rays and gamma ray wavelengths are strongly absorbed by the atmosphere, so again they should be located in space. But again, these types of telescopes are difficult to maintain and to repair. In terms of uses, X-rays and gamma rays can provide additional information about visible objects such as supernova remnants, and X-rays and gamma rays can observe non-visible objects and very energetic events such as neutron stars, black holes, pulsars and gamma ray bursts. Now, when we compare the resolving power of the telescopes, the X-ray and gamma rays have a much higher resolving power than the optical telescope because they've got a much shorter wavelength, linking it into the Rayleigh criterion for the same diameter dish. Now, in terms of the collecting powers, the X-ray and gamma ray telescopes have a much lower collecting power because they've got much smaller dishes that they use them for. However, X-ray and gamma ray sources tend to be extremely bright, so it can compensate for that. Now, the next question says, give one advantage and one disadvantage that radio telescopes have compared with optical telescopes. Then explain why most infrared observations have to be carried out above the atmosphere and what is meant by infrared windows. Then Sophia is a flying IR observatory housed in an aircraft with a telescope objective dish of diameter 2.4 meters. If it is observing an object at a wavelength of 24 micrometers, what is its minimum angular resolution, and how will this compare with that of an optical telescope with the same diameter observing at 510 nanometers? So pause the video now, then unpause the video when you want to go through your answer. So to answer this first question, you've got to think about the radio telescope compared to the optical telescopes in structure and when they operate. So the advantage of radio telescopes is it can operate day and night, while optical telescopes can only operate at night with clear skies and no visible radiation coming from the sun. The disadvantages, though, is that they operate at longer wavelengths because radio waves are longer, so therefore they'll have a poorer angular resolution than optical telescopes from the Rayleigh criterion. Now, most infrared observations are carried above the atmosphere because the infrared ray wavelengths are absorbed by the water vapor in the Earth's atmosphere. Now, infrared windows are parts of the infrared spectrum that are actually transparent to the Earth's atmosphere and therefore can reach the ground and ground-based telescopes without being absorbed. Now, we can work out the minimum angular resolution by making sure we're using the same wavelength, so convert our nanometers into meters and our micrometers into meters, pop them in there, and you can work it through to be 1 times 10 to the minus 5 and 2 times 10 to the minus 7 meters. Now, that therefore tells you that the optical telescope has an angular resolution of about 100 times better than the infrared telescope of the same diameter, mostly because of the wavelength of the light itself. Now, the next question says the IUE has a parabolic mirror of diameter 45 centimeters and focused UV radiation. For a wavelength of 120 nanometers, compare its minimum angular resolution and its collecting power with that of an optical telescope of the same diameter operating at 510 nanometers. Now, the detector on a UV telescope uses a photoelectric effect to convert UV photons to electrons. Calculate the energy of a UV photon with a wavelength of 120 nanometers and explain why it's necessary for most IR and all UV and X-ray telescopes to be positioned in space. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, once again, we work out a minimum angular resolution by using the Rayleigh criterion. So theta equals lambda over d. Pop it in there, and you get the IUE to be 2.7 times 10 to the minus 7 meters, and the optical telescope to be 1.1 times 10 to the minus 6 meters. Remember to keep our wavelength and our diameter into meters. So therefore, the resolving power of the optical telescope is about 10 times better than that of the IUE. Their collecting powers are the same, though, because if you notice from the information, resolution, they've got the same objective mirror diameter, the only factor that affects the collecting power. Now the energy of the UV photon is E equals hc over lambda, an equation from paper 1. Pop in all the values, convert your nanometers into meters, work it all through, and we get 1.66 times 10 to the minus 18 joules. Now infrared, UV and X-rays are heavily absorbed by the atmosphere of the Earth, so such telescopes need to be positioned in space above the atmosphere where these wavelengths are not blocked. The next question says, compare and contrast a CCD with a human eye in terms of a detector. So pause the video now, then unpause the video when you want to go through your answer. Right, so what's a comparison? For a human eye, the quantum efficiency, the number of photons in every 100 that will be detected by the detector, is about 1% for a human eye, but for a CCD is very high, 70% or above. So you're much more able to detect fainter objects. In terms of the resolution, the human eye is about 100 micrometers, but the CCD is about 10 micrometers, so you can see in much more detail the higher resolution, and this could be increased even further by using smaller pixels. But for convenience of use for the human eye, you just look, so it's very easy. But for a CCD, you'll need remote viewing. The images can be stored and analysed digitally and sent across the internet, but you can have longer exposure times than that of the eye because you can alter it, and the CCD will also detect a wider range of wavelengths than the human eye will, which will only detect visible radiation. The next question says, a student investigated how the nature of the image depends on the position of the object in front of a large converging lens. The diagram shows one position for the object. Complete a ray diagram to show how the image of the object is formed, then describe the nature of this image relative to the object. So pause the video now, then unpause the video when you want to go through your answer. Right, so what you can do here is you can see in this first response here the diagram that you would have to draw. So you'll get a mark for going through the center of the lens directly, and then a second one parallel to the axis. Then when it reaches the lens, it'll go through F on the right hand side, or you could go through F on the left hand side, and then when it reaches the lens it goes parallel to the axis. Now the image that you would form, as you can see on the screen, is going to be inverted. It's the wrong way around. It's magnified because the line is longer, and it's real because the lines actually cross. The next question says, explain with the help of a diagram what is meant by a refracting telescope being a normal adjustment. Your diagram should include the paths of two rays and show the position of the focus of the object and the eyepiece. Then a refracting telescope used by an amateur astronomer is in normal adjustment when looking at the moon. The telescope is 1 meter long and has a maximum useful magnification of 200. State the focal lengths of the objective lens and the eyepiece lens. Then a spacecraft is in orbit around the moon at an altitude of 50 kilometers. It is trying to find the landing site for one of the Apollo moon missions of the 1970s. The descent stage of the Apollo lunar module that was left on the moon is 4.3 meters wide. The orbiting spacecraft is equipped with a telescope with an angular magnification of 200. What is the angle subtended by the image of the Apollo descent stage by the spacecraft above the moon's surface? Then explain what is meant by chromatic aberration and how it is corrected in a convex lens. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you can see the diagram showing normal adjustment. It's the idea when you have your objective lens and your eyepiece lens that where the lines cross for both the objective lens and the eyepiece lens, it's in the same position if they're in normal adjustment. We also know here that FO is equal to 1 minus FE, so you can then work it through, and we know FO is what it's going to be 1 over 200, so you can work it all through and you get 955 millimeters. For the eyepiece lens, it's going to be the difference because you know the overall length is going to be 1000, so you know that the FO is equal to 995, so 995, so therefore the answer will be 5. Now in this next one, we've talked about this before, S is equal to R theta, so therefore theta is equal to S over R, so it's 14.3 over 50 times 10 to the 3. So you're looking at S, the length, and over R, the radius of the circle that you'll be producing for your angle. So therefore you work it through to be 2.7 times 10 to the minus 4 radians. Now chromatic aberration is due to the refractive index of the material being different for different wavelengths, so it'll be different colours. So the lens is unable to bring all visible wavelengths to the same point of focus. So this results in an image with fuzzy coloured edges, and so chromatic aberration can be reduced with the use of an achromatic doublet lens. So you would remove some of the different wavelengths. Okay, so it would be a composite lens of different types of glass that could bring two wavelengths like red and blue into focus at the same point. The next question says the diameter of the objective mirror of the Hale telescope is 5.1 meters and it's observing a star emitting a wavelength of 510 nanometers. What is the minimum angular resolution of the telescope in radians? What is the detail the telescope can detect on the surface of the moon? Planets have been detected around other stars. Estimate the diameter of a telescope objective lens required to resolve a Jupiter-sized planet orbiting the nearest star, which is about 4 times 10 to the 16 meters away. Assume you're observing at a wavelength of 550 nanometers. Then the Arecibo radio telescope has a dish diameter of 305 meters and has been used for observations using radio wavelengths as low as 4 centimeters. What is the theoretical angular resolution at this wavelength? How does this compare with the resolution of the Hale optical telescope? Then compare the collecting powers of the Lovell radio telescope at Jodrell Bank in Cheshire, UK, which has a diameter of 76.2 meters, the Arecibo radio telescope with a nominal diameter of 305 millimeters, and the Hale optical telescope, which has a mirror diameter of 5.1 meters. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, angular resolution is lambda over d, the Rayleigh criterion. Make sure we're in the same units, and we get 1 times 10 to the minus 7 radians. So the smallest detail that you can see is therefore going to be this particular minimum angular resolution multiplied by the distance to it. So therefore it will be 38 meters. In this next one, we know at a distance of 4 times 10 to the 16 meters, the angular resolution of a Jupiter-sized planet is going to be lambda over d. So you work it all through, 3.8 times 10 to the minus 7 radians. So therefore the diameter of the lens needs to be approximately, from using theta equals lambda over d, 145. Now the next one, the angular resolution, again you work through to be 1.3 times 10 to the minus 4 radians. Now the Hale telescope resolution is about 10 to the minus 7 radians from the previous questions. So that's about 1,000 times better. So despite the much larger sizes of the dishes, the angular resolution of the radio telescopes are a lot worse because radio wavelengths are a lot longer than optical ones, and theta equals lambda over d. And in the final one, remember what we've got to do, that the ratio of the collecting powers is the ratio of the squares of the objective diameters. So you would square all the different values, and you do each one like that to get 1 to 223 to 3500. The next question says, there's a supermassive black hole at the centre of the Milky Way galaxy. It is difficult to resolve images of the region around this black hole directly. Astronomers investigating the supermassive black hole detect radio waves at a frequency of 230 GHz. By correlating the information from several radio telescopes, they can obtain images with the same resolution as a single radio telescope with a diameter of 5,000 kilometers. So calculate the minimum angular separation which could be resolved by a radio telescope of diameter 5,000 kilometers detecting waves of frequency 230 GHz. So pause the video now, then unpause the video when you want to go through your answer. Right, in this one, how can we work it through? Well, we know the wavelength is going to be c over f, because with no c, it's going to be 3 times 10 to the 8. It's an electromagnetic wave. We've got f, it's 230 gigahertz. We turn that into hertz. So we get a wavelength of the radiation source. We can then say that the minimum angular resolution is the Rayleigh criterion. It's going to be theta equals lambda over d. We've just worked out lambda. We know d from the information is 5 times 10 to the 6 kilometers into meters. So we get 2.6 times 10 to the 10 radians. So 10 to the minus 10 radians, sorry. So the next question says, explain what is meant by the Rayleigh criterion. A telescope uses wavelengths in the range of 90 nanometers to 120 nanometers. Explain why this telescope must be located in space. Then table 1 shows information about 2 telescopes. Each telescope detects radio waves with a wavelength of 21 centimeters. Compare the performance of the telescopes in table 1 when both are used to observe the same faint radio objects. So pause the video now, then unpause the video when you want to go through your answer. So, to answer this first question, you've got to know the definition of the Rayleigh criterion. So it identifies the minimum subtended angle between two objects whose images can be resolved. So you've got to actually give more detail in this though, because it's the minimum angle when the central maximum of the diffraction pattern from one object coincides with the first minimum of the diffraction pattern of the second object. Learn that definition. It's very key and very crucial, not just the equation. Now, the advantage is that telescopes detecting UV or wavelengths smaller than visible light is very important because it indicates that it's going to be absorbed by the ozone layer, so therefore the atmosphere must be in space. The atmosphere is going to absorb it, so therefore the telescope must be in space. Now again, how do we link in our collecting powers? It is the square of the diameters, so we ratio the two, but we ratio the squares of the diameters, so it's 305 squared over 76 squared, so it's 16 times brighter. But just be careful about this, because there's no absolute conclusion, because the image from the receiver will be brighter, but Lovey will likely have a better detail because of the type of dish shape it has. There'll be no spherical aberration, so you could argue either way about which one shows the best image. The next question says, the Arecibo telescope has a dish diameter of 305 meters and has been used for observations using radio wavelengths as long as 4 centimeters. What is the angular resolution at this wavelength? Then compare the collecting powers of the Lovell radio telescope, which has a diameter of 76.2 meters, the Arecibo radio telescope with a diameter of 305 meters, and the Hale optical telescope with a mirror diameter of 5.1 meters. Then give one advantage or one disadvantage that radio telescopes have compared with optical telescopes. Then Sophia is a flying IR observatory housed in an aircraft with a telescope objective dish of 2.4 diameter meters. So if this is observing an object at a wavelength of 24 micrometers, what is its minimum angular resolution? How would this compare with that of an optical telescope of the same diameter observing at 510 nanometers? And then why is it necessary for most IR and all UV and X-ray telescopes to be positioned in space? So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, use the Rayleigh criterion, okay, and then you can work it through, and then you can actually get 1.3 times 10 to minus 4 radians. Sorry, not the Rayleigh criterion, rather you would use the ratio, well, no, sorry, it is the Rayleigh criterion, it's the wavelength over the diameter. The next one, we can do the ratios of the collecting powers by doing the diameter squared, so you work that one through. The advantage is that radio telescopes can operate day and night, while optical telescopes can only operate in night with clear skies, but the disadvantage is because radio waves are at longer wavelengths, the telescopes will have a poorer angular resolution than the optical ones. The minimum angular resolution again is the Rayleigh criterion, so therefore you can link it all through, and you can note that the optical telescope has a much better angular resolution than the infrared telescope. And then infrared, UV and X-rays are heavily absorbed by the atmosphere of Earth, so such telescopes need to be positioned in space above the atmosphere where these wavelengths are not blocked. Now the next question says, draw a ray diagram to show how a convergent lens can cause spherical aberration. Then draw a labeled ray diagram for an astronomical refracting telescope in normal adjustment. Show the 3 non-axial rays passing through both lenses, and then label the principal foci of the lenses. Then the next question is, the James Lick telescope is an astronomical refracting telescope. When in normal adjustment, the distance between the lenses of the telescope is 17.4 meters and the angular magnification is 750. Calculate the focal length of the eyepiece lens. The James Lick telescope can be observed to identify binary stars. 2 techniques available using the telescope are using a processed image from a CCD and direct observation using the naked eye. Compare the use of the CCD with the use of the naked eye to observe binary stars with this telescope. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you can see that in a ray diagram, you should have 2 pairs of rays drawn parallel to the principal axis, which are coming into different focus points or different foci. Now, the outer rays will focus closer to the lens than the inner rays, so you'll get different areas of focus, so you get different images formed when getting a blurred spherical image. The next question, you'd have both focal points labelled on the principal axis. FO is greater than FE. There'll be 3 off-axis rays through the objective lens correct as far as the eyepiece, and then 3 rays through the eyepiece correct with all parallel to the construction line as shown in the following diagram. Now in our next question, how can you work it through? Well, we know FO over FE is 750 because that's the angular magnification. We know the total length is FE plus FO, which is 17.4. We can then work that through and we get FE to be 2.317 times 10 to the minus 2 meters. Now in terms of comparing the two, the resolution is going to be limited by the diameter of the objective, so it'll make no difference, but the CCD does have a better resolution due to have smaller pixels, so the stars could be seen more easily as separate objects. The CCD will have a higher quantum efficiency and it can be exposed for a longer time, so therefore dimmer objects will be more likely to be observed, and it also can detect a wider range of wavelengths, so you can see more binary star pairs. The next question says, if the quantum efficiency of the human eye is about 4% and 10,000 photons fall onto a light-sensitive cell on the back of the retina, how many photons will the eye detect? Then summarise the main reasons why CCD is the detector of choice for modern astronomy. Then light intensity of 5.3 times 10 to the minus 3 watts per meter squared and a frequency of 3.9 times 10 to the 14 hertz fall on a pixel of area 4.2 times 10 to the minus 12 meter squared in a CCD detector in the focal plane of a telescope. The quantum efficiency of a CCD is 85%. How many photons of light are incident on the pixel per second, and how many of these photons are actually detected and produce a signal? So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, the detected photons is 4% of 10,000, which is 400. Now, CCDs have a higher quantum efficiency, so we can record fainter objects with shorter exposures. CCDs can store images electronically, you can send them over online for wider distribution. They can be processed as an image. They'll operate over a wider range of wavelengths than the eye, and they'll also have a linear response. And then finally, in this next question, power is going to be equal to the energy of the photon over time. So that's intensity times by area, so you can work it through to be 2.2 times 10 to the minus 14 watts. Now the energy of a photon is equal to HF, so you can say HF is going to be 6.6 times 10 to the minus 34 times by 3.9 times 10 to the 14, so you get 2.6 times 10 to the minus 19 joules. So in 1 second, that's 2.6 times 10 to the minus 19 watts, so the number of photons is therefore going to be 2.2 times 10 to the minus 14 over 2.6 times 10 to the minus 19, so that's in 1 second, that's 8.5 times 10 to the 4 photons. Now because it's 85% efficient, so therefore 0.85 times this value is going to be 7.2 times 10 to the 10 to the 4 photons detected every second. The next question says, the diagram shows a convergent lens being used as a magnifying glass. On the diagram, use a ruler to draw two rays from the top of the object which show how and where the image is formed. Represent the image by an arrow drawn in the correct position and then calculate the magnification produced by the lens. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you can see the ray diagram that should be produced. So you can see here, you get the ray parallel to the axis from the top of the object, and it's refracted through the focus and tracked back through the object. Rays through the centre of the lens will go straight through and be traced beyond the object. Then the rays join the top of the object to the focus on the left of the lens to be taken to the lens refracted parallel to the axis and traced back beyond the object, and you can draw in your arrow as shown here. You will then look at the length of the different objects and do the image length over the object length, and you get your answer out to be 3. The next question says, draw a ray diagram to show how a convergent lens can be used to form a diminished image of a real object. Label the object, image and principal foci of the lens on your diagram. Then a student experimented with a convergent lens whose focal length was known to be approximately 50 centimeters. She placed an object and screen at a fixed distance of 200 centimeters apart. With the lens 128 centimeters from the object, she observed a sharp image on the screen. Calculate the focal length of the lens. Then the lens was used as one of the components of a simple refracting astronomical telescope. State whether the lens formed the eyepiece or objective, given reasons for your answer. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you would draw a diagram as so. So you'd see that one line coming from the top of the object will go straight through the lens, being undeviated through the centre. And then one line will go through a parallel with the axis from the top, hit the lens and refract through F. Where the two lines cross, that is where the image is formed. We know from this information U is 128 centimeters, V is going to be equal to 200, the total length, minus 128 if you think about the distances between the image and the object of what U and V are, so that's 72 centimeters. We know 1 over F equals 1 over U plus 1 over V, the lens equation, so you can pop that all through and you get F out to be 46 centimeters. Now in this last one, okay, will it be an eyepiece or objective? Well, it'll be an objective lens because you know M is equal to FO over FE, and so for it needs to be magnified, FO needs to be greater than FE to get a positive, like a value bigger than 1 for M. So as we know, the telescope length is FO plus FE, so therefore if the lens must be an objective one, because otherwise if that wasn't the case, the telescope would be very, very, very long, which we don't want it to be. The next question says, draw a ray diagram to show how a convergent lens forms a magnified real image of a real object. Label the principal focus on your diagram. Then draw a ray diagram to show how a convergent lens forms a magnified virtual image of a real object. Label the principal focus on your diagram. Then a convergent lens of focal length 145mm is used to produce an image of an object placed 112mm from the lens. Calculate the image distance with an answer to the appropriate number of significant figures, and then state 3 properties of this image. So pause the video now, then unpause the video when you want to go through your answer. So in this first question, you've got to draw your diagram in like so. Like we said before, one line from the top goes straight through the center and undeviated. One line goes parallel to the axis and then refracts through F. Where the lines cross, that is where you get your image. In this next one, you're going to have your straight line again parallel to the axis going through F, and again that line going from the top going straight through the center of the lens. Because they're diverging away, you trace them back to where they came from. Dash the lines because it wasn't actually from there, it's just a mistake of the human brain to think it's coming from behind that object. Where those two virtual lines cross, that is where you get your image formed. Now in this next one, we know that 1 over f equals 1 over u plus 1 over v. Pop in all the values and we get v to be equal minus 492mm. Now you can use your diagram, but also the fact that v is a minus indicates it's going to be a virtual image, but from what you've seen before in the previous diagram, it's virtuous, magnified, and it's upright. Now the next question says, draw a ray diagram for an astronomical refracting telescope in normal adjustment. Your diagram should show the paths of 3 non-axial rays passing through both lenses. Label the principal foci of the 2 lenses. Then the Treptow Giant Telescope in Berlin is one of the longest movable refracting telescopes on Earth. Some of the properties are summarized below. Then calculate the focal length of the eyepiece lens and the objective lens of the Treptow Giant Telescope, and then the images formed by the refracting telescope can suffer from chromatic aberration. Draw a labeled diagram to show how convergent lenses cause chromatic aberration. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you can see the diagram is shown here. So you can see that the rays are off axis to get the mark. You can see that they've refracted through the objective lens there. They've met at the point where FO and FE there. They'll then hit against the eyepiece lens, and then they'll refract parallel to the construction line as drawn before. We know FO plus FE is 21. So FO over FE is 210 from the information given. So you can say 211 for FE equals 21. So FE is 0.10 meters, so therefore FO must be 21 meters to get that final value out. Now again, how do we show chromatic aberration? It's that we're showing that when rays are going through that lens, that unfortunately that the red wavelength will refract at a longer distance than the blue wavelength, which will refract shorter. So you get 2 different foci. The foci of the blue wavelength will be closer to the lens than the foci of the red wavelength, so you get those differences in focal points for the wavelengths. The next question says, draw a ray diagram for an astronomical refracting telescope in normal adjustment. Your diagram should show the paths of 3 non-axial rays through both lenses. Label the principal foci of the 2 lenses. Then an early form of this telescope was built by Johannes Helvetius. It was 3.7 meters long and had an angular magnification of 50. Helvetius used it to produce one of the earliest maps of the moon's surface. Calculate the focal length of the objective lens and the eyepiece lens in an astronomical telescope of length 3.7 meters and an angular magnification of 50. Then the Triesnecker crater on the moon has a diameter of 23 kilometers. Calculate the angle subtended by the image of this crater when viewed through a telescope of angular magnification 50 on the Earth. Then early refracted telescopes suffered significantly from chromatic aberration. Draw a diagram to show how a single convergent lens produces chromatic aberration. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, as the diagram showed in the previous question, 3 parallel off-axis rays through the objective lens. The rays continue through to the eyepiece, emerging parallel to the construction line, and you label your foci where the 2 lines have crossed over, the FO and the FE. We know FO plus FE is 37, FO over FE is 50, so we can work out FO to be 3.6 meters, similar to the previous question, and FE is the previous equation, and FE is 0.074 meters. In this next one, we know that S equals R theta, so therefore theta is S over R, S being the diameter of the object and R being the distance to the object, put them both in meters, or you can keep them in kilometers to be fair, because there'll be a ratio. So we 6 6 times 10 to the minus 5 radians. We know m is theta I over theta O, so we work that through to equal 3 times 10 to the 3 radians. And then the idea is with chromatic aberration that there'll be a wavelength, red wavelength will have the focus further away from the lens than the blue wavelength will as well. The next question says, draw a ray diagram for a Cassegrain telescope. Your diagram should show the paths of 2 rays up to the eyepiece lens. A spacecraft passes Pluto at a distance of 12,500 kilometers. The telescope on board has an aperture of diameter 0.21 meters and operates at a wavelength of 450 nanometers. Discuss whether this telescope is suitable for studying a crater with diameter of approximately 1 kilometer on Pluto. Then the Hubble's telescope has an aperture of diameter 2.4 meters. Compare the collecting power of the Hubble telescope with the telescope on the spacecraft in 1.2. Then astrophysicists had to decide whether to use a reflecting telescope or a refracting telescope on the spacecraft in 1.2. Which type of telescope would be used? So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you have your diagram of your Cassegrain telescope with both mirrors correct and the 2 rays correct. So it looks something like that. Your rays are parallel, they hit the primary mirror, they reflect, they hit the secondary mirror. The lines cross just before they hit the gap in the primary mirror, they then hit the lens and refract through the lens. We know that resolution is going to be the wavelength over the diameter, keep them both in meters, so you get 2.14 times 10 to the minus 6 radians. The smallest detail is therefore going to be equal to the resolution times by the distance it's away from us, so you get 27 meters, which is suitable because that's about 1/40th of the crater's total size. Now in this next one, collecting power is proportional to area, so it's a ratio of the diameters squared, so it's 2.4 squared over 21 squared, which is 130, so it's 130 times bigger. Now the problems of refractors are that they can suffer spherical aberration and chromatic aberration. Reflectors are lighter and reflectors are shorter, so therefore the mirror wouldn't suffer from chromatic aberration. But an issue with reflectors is that the secondary mirror could reduce the brightness, block out some of the light and cause diffraction effects as well. So you've got to pick which one based on the comparison, but it really should be the reflector. The next question says, draw the ray diagram for a Cassegrain telescope. You should draw paths of 2 rays initially parallel to the principal axis as far as the eyepiece. A telescope design very similar to the Cassegrain was first proposed by James Gregory in 1663. His telescope design was also the first to include a parabolic primary reflector. The use of a parabolic reflector overcomes the problem of spherical aberration. Draw a diagram to show how spherical aberration is caused by a spherical mirror. Then the first telescope constructed to this design had a primary mirror of diameter 0.15 meters. Calculate the minimum angular separation which could be resolved by this telescope when observing point sources of light of greater than 630 nanometers and state an appropriate unit. Then the astronomer Edmund Halley claimed to have used his telescope to observe the Cassini division, a dark band in the rings of Saturn. Calculate the angle subtended by the width of this band at the Earth and comment on whether Halley's claim is likely to be valid. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, as we said before, you would draw the following diagram to show the Cassegrain arrangement and the following diagram to show the spherical aberration. Remember, all the lines are parallel to the primary mirror, and then when they reflect off the primary mirror at slightly different angles, therefore they'll cross over at different points, they'll have different foci. If you are further from the axis, their foci occur closer to the mirror. In this next question, we use the Rayleigh criterion. Theta equals lambda over d, same unit, so taking nanometers out into meters, so you get 4.2 times 10 to the minus 6 radians, because that's what we get our values out in the Rayleigh criterion. And this last one, S is equal to r theta, so you can work out theta, which is 3.43 times 10 to the minus 6 radians. Leave your conclusion that it's unlikely to be valid because this angle is smaller than the minimum angular separation we calculated previously, so it's unlikely to have been true. The next question says, draw a ray diagram to show the path of 2 rays traveling parallel to the principal axis through the Cassegrain telescope. With the aid of the ray diagram, explain what is meant by spherical aberration when applied to a concave mirror, and with the aid of a ray diagram, explain what is meant by chromatic aberration. So pause the video now, then unpause the video when you want to go through your answer. Right, as we said before, with your diagram, the rays reflect the concave or primary mirror, they reflect the convex mirror, and they just cross before the front of the eyepiece lens. The next one, we have different focal points at different distances from the axis, with the shortest focal length for those periaxial rays, like we said before. And then for chromatic aberration, lights at different wavelengths refracted to different foci, with this shown refraction for blue much closer to the lens than that of red. The next question says the observations of Ceres has been made by the Infrared Telescope Facility in Hawaii. The IRTF consists of a Cassegrain telescope with an objective diameter of 3 meters. Draw a ray diagram for a Cassegrain telescope. The IRTF includes a camera capable of detecting infrared radiation with wavelengths 1 micrometer to 5 micrometers, calculating radians, the smallest angle the telescope could resolve. And then Table 1 summarizes some properties of Ceres, the largest object in the asteroid belt between Mars and Jupiter. Discuss the level of detail IRTF will be able to detect on the surface of Ceres when Ceres is at as close as possible distance to the Earth. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, like we said before, this is the ray diagram for a Cassegrain or a reflecting telescope. Remember, the rays must cross after the secondary mirror. Okay, the next question, use the Rayleigh criterion. It's lambda over d, same units. Now again, the smallest wavelength will give us the smallest angle we can resolve from the equation, so we then say it's 3 meters. In this next one, because you've got the distance there, you can work out that the minimum angular resolution is going to be better or smaller than the size of the asteroid, so you'll get details of about 1/10 the angular size of Ceres, which can be resolved by the telescope. The next question says, the concave mirrors used in some reflecting telescopes can suffer from spherical aberration. Draw a diagram to show what is meant by spherical aberration when it is produced by a concave mirror. Then the International Ultraviolet Explorer, the IUE, and the Grand Telescopic Chimeras GTC are two examples of a reflecting telescope. The table below summarizes some of the properties of the two telescopes. Compare the two telescopes in terms of location, collecting power and minimum angular resolution. Include calculations to support your comparisons. And the charge coupled device, the CCD, is an important part of the detection system of many modern telescopes due to its high quantum efficiency. Explain what is meant by the term quantum efficiency and compare the quantum efficiency of a CCD with that of the eye. So pause the video now, then unpause the video when you want to go through your answers. Right, in this first one, again, what's the diagram to show spherical aberration? You've got a concave mirror with parallel incident lines, and they reflect at different focal points because they're hitting the mirror at different angles. Now the rays further from the paraxial line, the one in the middle, will be brought focus nearer to the mirror. So you'll see that they'll be crossing over at different points. Now in our next one, how can we work it through? So first let's think about the location. Well, light has to travel through some of the atmosphere to reach the GTC because it's on the ground. So that affects the amount of light arriving and the resolution. Now because the IUE is in orbit, it'll need its own power source and will need to send information to the ground for analysis. And its position is quite inconvenient and expensive if there needs to be repairs made or to service the actual telescope. Now in terms of collecting power, remember that collecting power is proportional to d squared, so we can say that the ratio is the 10.4 squared over 0.54 squared, so it's 530. So then we'll say the GTC has 530 times the collecting power, so it's going to be better because it'll give you a brighter image. Now the minimum angular resolution links to the Rayleigh criterion of theta equals lambda over d, so you do is proportional to 1 over d. So when you work that through, you get a value of 0.2. So that tells us that the GTC is 5 times better at resolving than the IUE, and so therefore it's going to be better because it'll give a clearer image. Now in this final question, remember what the definition is for a quantum efficiency. It's the number of photons actually detected by the detector divided by the total number of photons incident. Now I know that for CCDs that the quantum efficiency is 80% or above. It's increasing with the advent of modern technology, but the eye is about 1%, so therefore that the CCD is a much more quantumly efficient device. So that brings an end to our revision session today. Hopefully if you've been successful, you can answer A-level physics examination style questions on telescopes. You can assess your understanding of A-level physics on telescopes and then understand what topics you need to improve upon for A-level physics. So thank you so much for listening to this revision session for AQA A-Level Physics Paper 3 on the topic of telescopes for the astrophysics option. Thank you so much and have a lovely day. Let's now have a look at some questions on the stars topic of the astrophysics option for AQA A-Level Physics. So the first question says, explain what is meant in astronomy by a parallax angle. Then a measurement of a parallax of a star 61 Cygni in the constellation Cygnus is found to be 0.316 arcseconds. What is its distance from the Earth in the following units? In parsecs, astronomical units, and in light years. Then Proxima Centauri, a red dwarf 4.2 light years from the Earth is our nearest star other than the Sun. What is its distance from the Earth in parsecs, and what would its parallax angle be? So pause the video now, then unpause the video when you want to go through your answer. Right, so you've got to be able to define what we mean by parallax angle. So the parallax angle by definition is half the angle between the direction of a nearby star from the Earth at one time of the year and then its direction from the Earth 6 months later, half the orbit later. Now in this next question you've got to be able to convert from arc seconds from arc seconds into parsecs, and you do that by doing the distance in parsecs is 1 over the distance in arc seconds, so we get 3.16 parsecs. You've got to be able to convert between parsecs and astronomical units. There's a conversion factor given to you, so when you work it through it's 650,000 AU, and then you've got the very famous conversion factor that 1 parsec is equal to 3.26 light years, so that works out to be 10.3 light years. Again, we can look at to work out the distance of Proxima Centauri using that particularly famous conversion factor, so it's 1.3 parsecs. And then remember, we can work out the parallax angle because it's 1 over the distance, okay, to the star in parsecs, and it gives you the angle in arc seconds, so it's 1 over 1.3, which is 0.77 arc seconds. The next question says, firstly, explain what is meant by stellar parallax, then calculate the distance from the Earth in parsecs to a star that makes a parallax angle of 0.18 arc seconds. Then use the data below to show the Earth is approximately 8 light minutes from the Sun, and then Proxima Centauri is around 1.3 parsecs from the Earth. So pause the video now, then unpause the video when you want to go through your answer. Right, again, let's go to the definition of parallax. Well, it's the technique used to determine the distance to stars less than 100 parsecs away from the Earth, and it's the motion or the apparent motion of nearby stars against the fixed background of the distant stars. Now again, how can you work out the distance? Well, distance in distance in parsecs is 1 over the parallax angle in arc seconds, so it's 1 over 0.018, which is 56 parsecs. The next one, you can work out the distance from the Earth to the Sun as 1 astronomical unit, so it's 1.50 times 10 to the 11 meters. So therefore the time taken is going to be 1.50 times 10 to the 11, the distance, divided by the speed. First, for light is 3 times 10 to the 8, which is 500 seconds, which is approximately 8 light minutes. Then Proxima Centauri is around 1.3 parsecs from the Earth. Okay, so how can we then work that out? How can we show that? Well, we can work it through by saying it's 4.24 light years. We know the conversion factor, so we can then work out this distance in parsecs. The next question says, how much brighter is a magnitude 1 star compared to a magnitude 2 star? Then star A has an apparent magnitude of 3.44 and star B has an apparent magnitude of 5.72. Show that star A appears to be around 8 times brighter than star B. Then Aludra in the constellation Canis Major has an apparent magnitude of 3.5 and is 3,200 light years from the Earth. Calculate the absolute magnitude of Aludra. Then a type 1a supernova in a galaxy has a peak absolute magnitude of minus 19.3 and a peak apparent magnitude of 2.2. Calculate the distance to the galaxy in parsecs. So pause the video now, then unpause the video when you want to go through your answer. Right, so for this first one, you've got to be able to understand you can work out the difference in brightness by doing 2.51 to the power of the difference between the two magnitudes. So it's 2.51 to the power of 1, because that's the difference between 2 and 1. So therefore it's 2.51 to the power of 1, which is 2.51. So the magnitude 1 star is 2.51 times brighter than magnitude 2, because the lower the number, the brighter the magnitude in this particular scale. The next one, you will find once again the difference in the magnitude, so it's 2.51 to the power of 2.28, which is 8.2. The next one, you've got to use the equation, which is small m minus big M is equal to 5 log d over 10, where small m is the apparent magnitude, big M is the absolute magnitude, and d is the distance in parsecs. So the first thing you've got to do is use that conversion factor and change the distance from light years to parsecs, pop it into the equation, work it through, and you get minus 6.5. So it's going to be very bright because it's a very negative value. Then the next one, again, we're using the same equation again, but this time we're having to make d the subject. So how you can do that is remember to make log to the power, okay, one of the subjects, and then you can get rid of that log to the power by doing 10 to the power. So it would work through like so. So we get rid of that log value. So you can work through d is equal to 10 times by 10 to the power of m minus m over 5, pop in all the values, and we get to 200,000 parsecs. The next question says, using Stefan's law, compare the luminosity of one star with another that has, firstly, double the surface temperature in the same radius, then double the radius and half the surface temperature, then half the mass, the same density and 3 times the surface temperature. Then the sun has a radius of approximately 700,000 kilometers and a surface temperature of 5,800 Kelvin. Calculate the energy radiated by the sun during 1 year. Then the peak wavelength emitted by a distant star with a luminosity of 4.85 times 10 to the 31 watts is measured as 305 nanometers using a diffraction grating. Calculate the radius of this star. So pause the video now, then unpause the video when you want to go through your answer. Right, so this first one is using the Stefan's law and looking at how the factors link to each other. So Stefan's law is that the brightness or the luminosity is equal to sigma a t to the 4, a b and 4 pi r squared, because that is the surface area of a sphere, which we assume a star to be. So that tells us if we keep everything else constant but double the surface area, well therefore, okay, L will increase by a factor of 16 because it's 2 to the power of 4. The next one, we're doubling the radius and half in the surface temperature. Well, if L is proportional to t to the 4, if t halves, then L will decrease by a factor of 16, 2 to the 4. But L is proportional to r squared because a equals 4 pi r squared. So if r doubles, L increases by a factor of 4. So therefore it decreases by a factor of 16, increases by a factor of 4. So therefore the luminosity will decrease by a factor of 4. The next one, so if we look at the different ideas completely, L is directly proportional to t to the 4. So if t increases by a factor of 3, L will increase by a factor of 81, 3 to the power of 4. L is directly proportional to r squared. So if r decreases by a factor of 3 to the square root 2, because as mass halves, volume halves for a constant density, and volume is 4 over 3 pi r cubed. Therefore, L will decrease by a factor of 1.6. So that's 3 square root. That's 3 square root 2 squared. So therefore, what happens is if one increases by a factor of 81, the other decreases by a factor of 1.6, it overall increases by a factor of 51. This next one, we're going to use Stefan's law again. So that is brightness is equal to sigma a t to the 4, where a is 4 pi r squared. Okay, you pop in all the values, you work it through, and you get 3.95 times 10 to the 26 watts, because the luminosity, the brightness, is the power. So therefore the power, we know, is equal to energy over time. So energy is power times time, or luminosity times time. So we multiply the luminosity value by the time in 1 year. So we work out the number of seconds in the year to do that. So we get 1.25 times 10 to the 34 joules. Then in this last question again, we're now having to use the Wien's displacement law. So lambda max times by t equals 2.93 times 10 to the minus 3. So we can work out the absolute surface temperature in Kelvin by working those through with those values. Remember, nanometers is 10 to the minus 9. So we get 9,800 Kelvin. We then pop it into the equation for Stefan's law, but we make R the subject. So we work it all through, pop in the values, and we get 8.59 times 10 to the 10 meters. So in our next question, it says calculate the Schwarzschild radius for firstly the Earth, secondly the Sun, third an average human being, and then fourth use the idea of escape velocity and kinetic energy and potential energy to derive the expression for the Schwarzschild radius. So pause the video now, then unpause the video when you want to go through your answer. Right, so how to answer this question? Well, you've got to look for your equation for the Schwarzschild radius, which is the effective radius of a black hole. So the Schwarzschild radius is 2gm over c squared. So we can pop in all the values. Remember, g is a constant 6.67 times 10 to the minus 11. C is a constant 3 times 10 to the 8. Pop in all the values and you get your Schwarzschild radius out for the Earth, the Schwarzschild radius out for the Sun. Now, just to clarify, the masses of the Earth and the Sun are given on the equation sheet for AQA A-Level Physics. For an average human being, you're going to have to estimate what the mass could be, anywhere between 60 and 80 kilograms. I've used 75, so we get our answer out there. Now, how do we derive the Schwarzschild radius? Well, what we've got to say is, with escape velocity, when you've done this for gravitational fields, you can say that the kinetic energy is equal to the gravitational potential energy. Again, we can't use mgh for the gravitational potential energy because g, the strength of gravity, will change as you move through towards the black hole. So we've got to use big G, big M, M over r. You then pop in all your values. Remember, v will turn into c because we're looking at the speed of light, because that's we look to see that can escape the black hole. Okay, and that's going to happen at the effective radius, because the fastest possible speed you could have. So you could then say half mc squared equals gmm over r. Small m cancels through on both sides. We then rearrange to make r the subject, and that is the Schwarzschild radius. The next question says, explain why the Chandrasekhar limit must be exceeded in order for the core to form a neutron star. The pulses received from LGM1 came from a pulsar 2.18 times 10 to the 19 meters from the Earth. Calculate the time taken for a pulse to travel from the star to the Earth. Then LGM1 is estimated to have a radius of 1.4 million times smaller than our Sun. Assume LGM1 has a density similar to that of a typical neutron star. Calculate its mass. So pause the video now, then unpause the video when you want to go through your answer. Right, so what is the Chandrasekhar limit? It's the idea that mass must be large enough to provide a gravitational attraction strong enough to overcome this electron degeneracy pressure. So the neutron star will form at the Chandrasekhar limit because the electrons can't be squashed any closer together because they have their own integrity. So as a result, you need the gravitational attraction to be strong enough to overcome that degeneracy pressure. So therefore you've got your Chandrasekhar limit, that mass large enough to do so. This next question, again, it's a nice one because the pulses from pulsar are radio. Okay, so therefore it's going to be the speed of an electromagnetic wave, 3 times 10 to the 8. Time is distance over speed. You've got the distance, you've got the time, you've got the speed, so you can work out the time it takes to reach us. Now in this last question, we can work out the density. So density is mass over volume, and volume is 4 over 3 pi r cubed because we assume it to be a sphere as a star. So therefore our mass is going to be density times by volume. So you can put that in together. So therefore we can work out what the radius of the star is going to be, because it's going to be 1.4 million times smaller than our Sun. So you take the radius of the Sun given to you on the AQA equation sheet and you work out the radius to be 400 meters. You can then pop that into the equation you just derived there and you get your answer out to be 5.2 times 10 to 25 kilograms. The next question now says, in the 16th century, the astronomer Tycho Brahe made measurements of stars in the night sky. He measured the angle of a range of stars above the horizon. For each star, he measured the angle over a period of time to determine a parallax effect. First, he described how the stellar parallax is used by astronomers. Tycho Brahe concluded that the Earth was motionless at the centre of the universe as he was not able to detect any stellar parallax. Suggest why he was not able to detect any stellar parallax. Tycho Brahe was one of the first astronomers to observe a supernova. Supernovas are used as a type of standard candle. What is meant by a standard candle? And then describe how standard candles can be used to determine the distance to nearby galaxies. So pause the video now, then unpause the video when you want to go through your answer. Right, so the first one is explain what stellar parallax is. So that's a star is viewed from two positions at 6-month intervals, half the orbit of the Earth. So the star is viewed from opposite ends of the diameter of the Earth's orbit. So the change in angular position of the star against the backdrop of the distant or the fixed stars and galaxies is then measured. We can then use trigonometry to calculate our distance to the star with the right angle triangle. We can work it through to be the diameter of the radius of the Earth's orbit must be known for us to work it out because it's one of the sides of our right angle triangle. Now the next one, why detecting stellar parallax? Because those stars at the centre of the universe, which he thought was the point, were so far away that you couldn't determine any change in positions. They were too small to actually be measured with the naked eye in the 16th century. Now a standard candle, you've got to know the definition. It's a stellar object of known luminosity or known absolute magnitude. Now you can work out distances with standard candles, because if you can measure the intensity of radiation from the standard candle, you can work out its apparent magnitude, you know its absolute magnitude, so therefore you can work out its distance. The next question says, by what factor is a star of magnitude 1 brighter than one of apparent magnitude 3? The table 1 below shows a number of stars and their apparent magnitudes. Rank them in increasing order of brightness. How much is star the Canopus brighter than Altair? Then the Sun has a luminosity of 3.90 times 10 to 26 watts. What is its brightness in watts per meter squared at firstly the top of the Earth's atmosphere and then secondly at the surface of Pluto? So pause the video now, then unpause the video when you want to go through your answer. Right, so like we said before, to work out the difference in brightness, it's 2.51 to the difference in the magnitude. So it's 2.51 to the power of 2, so that is 6.3. Now, the order of brightness, the brightest object is the most negative number, and the dimmest object is the highest number. So the star should be ordered from most negative as the brightest to the least brightest, the dimmest at the biggest value. Now again, how much brighter is Canopus than Altair? So you do 2.51 to the power of the difference in the magnitudes, and it works through to be about 5.2 times brighter. Now in this next one, you'll have noticed from the equation it says in watts per meter squared. So to work out the brightness, you're going to have to take the luminosity of the sun, which is given to you, and then divide it by the area over which is over. So it's 4 pi r squared, because we're going to assume the ray is going to go as a sphere, and we know r to be the distance between the sun and the object. So we pop those into the equation, and we get 1380 at the Earth, but at Pluto we get 0.88 watts per meter squared. The next question says, explain the difference in meaning between apparent and absolute magnitude. The star Procyon A has an apparent magnitude of plus 0.34 and is at a distance of 3.5 parsecs. What is absolute magnitude? The star Regulus has an apparent magnitude of plus 1.35 and an absolute magnitude of minus 0.30. What is its distance modulus? How far away from us is Regulus in parsecs? And then why is there a limit to the distances that can be measured using parallax? So pause the video now, then unpause the video when you want to go through your answer. Right, you've got to know the difference between apparent and absolute magnitude. So apparent magnitude is the brightness of the object from Earth, while absolute magnitude is the apparent magnitude an object would have if it was located at a distance of 10 parsecs away from the Earth. Now the next question, we've got to use that equation, small m minus big M equals 5 log d over 10. Pop in all the numbers and you get 2.64. The distance modulus is that small m minus big M value that you can get. So you're just subtracting the two numbers, but remember you're subtracting a negative, so it's actually going to add, so therefore it's 1.65. The next one, how can you work it out? Well, you can then use that in that equation, m minus m equals 5 log d over 10, work it through, and we get 21.3 parsecs. Remember how to get rid of that log is going by 10 to the power. And then why is there a limit to distances that can be measured in parallax? Because as we said before, as the distance to an object increases, the parallax angle becomes smaller because the apparent motion of a star gets less, so therefore it looks like it isn't moving and can't be measured. The next question says, the star Arcturus has a radius 25 times the radius of the Sun and a surface temperature of about 4,300 Kelvin. Estimate the luminosity of Arcturus. The star Rigel has a luminosity 66,000 times that of the Sun. If its surface temperature is 11,000 Kelvin, estimate the radius of Rigel. And then what is the peak wavelength emission of Rigel? So pause the video now, then unpause the video when you want to go through your answers. Right, in this first one, we're trying to work out luminosity. So it's got to be Stefan's law. So it's sigma AT to the 4. So you pop in all those values. Remember, A is 4 pi r squared because it is this sphere. Remember, it's 25 times the radius of the Sun. Pop in all the values. It's 7.4 times 10 to the 28 watts. Again, this next one, we've been given luminosity now. So at this point, we're rearranging the equation, making R the subject and working it through. So we get 5 times 10 to the 10 meters. And then the peak wavelength we can do with the Wien displacement law. Lambda max times by T equals 2.9 times 10 to the minus 3. Pop in all the values, work it through, and we get 2.6 times 10 to the minus 7 meters. The next question says, Sirius is the brightest star as seen from the Earth and has a surface temperature of 9,940 Kelvin. Calculate the peak wavelength emitted by Sirius and use this value to sketch a blackbody radiation curve for Sirius. Then Arcturus is the fourth brightest star as seen from the Earth and has a surface temperature of 4,290 Kelvin. Describe two ways in which the blackbody radiation graph will be different for Arcturus. So pause the video now, then unpause the video when you want to go through your answer. Right, so for this first one, you've got to be able to work it through what the peak wavelength would be by doing the Wien displacement law. So lambda max equals 2.9 times 10 to the 3 over t, so we get 2.9 times 10 to the minus 7, so that's about 300 nanometers approximately. Then you've got to be able to sketch what a blackbody radiation curve looks like. Now the blackbody radiation curve should have a peak which is shifted to the left hand side, but it's a continuous curve as shown, and it should peak at about 300 nanometers. Now what would happen if you have something with a lower surface temperature or a higher surface temperature? So what would happen is, if Sirius has the higher surface temperature, it's going to have a bigger radiation emission, because that's a law of radiation. So therefore what would happen is, firstly the intensity would be higher for all the values for Sirius because it's given off more radiation. Okay, however the peak wavelength for Sirius would therefore be a lot shorter as well. So if we go back to Arcturus, the peak wavelength would be bigger, okay, than that of Sirius, but its intensity at all values will be much lower. The next question says, sunspots are cooler spots on the sun's surface that have a temperature of around 3000 to 4500 Kelvin compared with the average surface temperature of 5800 Kelvin on the rest of the sun's surface. Uses information to explain why calculations using the inverse square law for the sun might be inaccurate. The data below gives some of the properties of the star Rigel in the constellation Orion. Calculate the peak wavelength in the blackbody curve of Rigel and calculate the surface area of Rigel in meters squared. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, it's an important idea you understand the assumptions of the inverse square law, and that is that you're assuming that the power output is constant throughout the process and also constant in all directions as well. This won't be the case because with sunspots the temperature is lower, so we know from the Vine displacement law that therefore if the temperature is lower, the power emitted by that particular star will be lower, so the inverse square law will not be true. This next question, we're looking for peak wavelength, so we've got to use the Vine displacement law. Lambda max times by t equals 2.9 times 10 to the minus 3. We work at all the values and we get 2.6 times 10 to the minus 7 meters. This next one, what we've got to do is we're trying to work out the surface area. So in this one we can use the Stefan's law, so we can say that power or luminosity equals sigma at to the 4. A, we can therefore say, is the power or luminosity over sigma t to the 4. However, we've got to be able to work out what this power is first. So we've got to use the inverse square law, and the inverse square law says that the power will be the intensity multiplied by pi r squared, or pi d squared as I've written down there. Now what is d? The distance of this is going to be, well, you're going to have to work it through, so therefore it's the distance between us and Rigel, so we're going to convert that into meters if you want to work out a value in meters squared later. So we convert from light years into meters. That conversion is given to you on the equation sheet. You then pop it in to work out the power, pop that into the Stefan's law, so you get out 3.0 times 10 to the 22 meters squared. The next question says, firstly, explain what is meant by a parsec and draw a labelled diagram in support of your answer. Then the Hipparcos satellite used the parallax method to measure the distance to more than 100,000 stars with the precision of 0.002 arc seconds. Calculate the distance in meters, the maximum distance measured by Hipparcos, and give the answer into the appropriate significant figures. Then the star Alpha Capricorni is in fact two stars that appear very close together. Some of the data about the two stars is summarised on the screen. Firstly, explain how the data in the tables indicates the two stars are not part of a binary system, and then explain why the angular separation of the two star changes when observed from the Earth during a 12-month period. So pause the video now, then unpause the video when you want to go through your answer. Right, it's very important that you can draw a labelled diagram of the right angle triangle produced to work out the parsec. So you'll notice we've got a right angle triangle there, and the distance between us and the actual star is given as a parsec. You know the distance between the sun and the earth below is going to be 1 astronomical unit. That's the definition of the astronomical unit. And then in that case, the angle produced for half of the particular half of the orbit is going to be 1 arc second. So you can see there in that particular diagram. In this next one, well, what did we know before? We said that distance in parsecs is equal to 1 over the parallax angle in arc seconds. So therefore it's 1 over 0.002 because that's the precision. So therefore we've got a precision of about 500 parsecs to work it through. Now we can put that into meters by converting from parsecs into meters. We get that conversion on the equation sheet, so it's 2 times 10 to the 19 meters. Now, they're not part of a binary system because you'll notice they've got a very, very big distance between them. So as a result, they're 178 parsecs apart, which is a massive distance. Now, a binary system is when the two stars are co-orbiting each other, and they can't be co-orbiting at such a great distance. So they can't be a binary system. Now, why does that change? Well, the more the amount of parallax you will get depends on the distance you are from the Earth. The further you are away, the less parallax effect you will get. So the more distant star, alpha 1, will not move as much as alpha 2. The next question says, Epsilon Arandi is a star 9.94 times 10 to the 16 meters from the Earth. It has a diameter of 1.02 times 10 to the 9 meters. The apparent brightness of Epsilon Arandi is measured on Earth to be 1.05 times 10 to the minus 9 watts per meter squared. Firstly, calculate the luminosity of Epsilon Arandi, then calculate the surface temperature of Epsilon Arandi, and then state any assumption made in your calculation. So pause the video now, then unpause the video when you want to go through your answer. Well, we're trying to work out the luminosity here, so what we can do is we can use our inverse square law because we've been given the brightness, so we know that brightness is equal to the luminosity over 4 pi r squared from the inverse square law. So therefore we can rearrange that and work out the luminosity by popping in all the values. Now again, remember, okay, that we can work out the value of r very carefully by looking at how far away it is from the Earth as shown there. So you can work out our luminosity 1.30 times 10 to the 26 watts. We can then work out the surface temperature by using Stefan's law, because we know that the luminosity is equal to sigma a t to the power 4. Now we know that a equals 4 pi r squared, so we can pop it all through. We get 5150 Kelvin. It's also very, very important to note that you're given the diameter in the information, but the question wants you to use the radius because we're working out the area of the surface area of the star, so it's 4 pi r squared. So just be careful about that. Now the assumption we make is for Stefan's law to be true, it must be a black body emitter. We're also assuming that because we're using our equations that it's spherical, it's a sphere, and that also the surface temperature is uniform, so we can use the inverse square law. The next question says, Bellatrix and Betelgeuse are stars in the constellation of Orion. Some of their properties are summarized below. Firstly, explain what is meant by absolute magnitude. Work out which of the stars is closer to the Earth. Explain your answer. Calculate the wavelength of the peak intensity in the blackbody radiation curve of Bellatrix, and then sketch the blackbody radiation curve for Bellatrix with a labelled wavelength axis with a suitable scale. So pause the video now, then unpause the video when you want to go through your answer. Right, learn the definition of absolute magnitude. It's the brightness of a star as it would appear from a distance of 10 parsecs from the Earth. The two stars, which one is going to be closer? Well, the answer is going to be Betelgeuse. Now you can see that because the Bellatrix has a much more negative absolute magnitude, it must be a lot brighter than Betelgeuse, but it only appears a bit brighter from the perspective of the Earth, indicating that it must be much further away because it doesn't appear to be much brighter than Betelgeuse, even though it should be a lot brighter, so therefore Betelgeuse must be closer. Now to work out the wavelength, we've got to use our blackbody radiation curve ideas to look at the Wien displacement of lambda max times by t equals 2.9 times 10 to the minus 3, pop in all the values, and we get 1.32 times 10 to the minus 7 meters. Now that tells us we can use our radiation curve because that's where the peak should be. It's steeper on the left hand side compared to the right hand side, and therefore it gives you a continuous spectrum as well. The next question says, Table 1 summarizes some of the information about 4 stars in the constellation Cassiopeia. Firstly, which star has the highest surface temperature, and then Figure 1 shows the intensity received at Earth from 2 of the stars plotted against wavelength. The effect of absorption by the Earth's atmosphere is not shown. Discuss what information can be found from Figure 1 about the temperature and the colour of these stars. Support your answers with suitable calculations. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you can look at which one is going to have the highest surface temperature by looking at the colour of the star. So you've got to be aware that the bluest stars on the blue end of the spectrum have the highest temperature, and the ones on the reddest part of the spectrum have the lowest temperature. So therefore the answer is Tish, because it is blue. Now the next one, from this diagram, you can work out what the peak surface temperature is going. Sorry, the surface temperature is going to be from the peak wavelength. So you can use the Wien displacement displacement law for each of them to work out what your peak wavelength of each of them should be. Sorry, the peak wavelength, just the surface temperature of each star should be. Now you'll notice as well that from the information given from the peak wavelength on the graph, that shader has a longer wavelength than cap, so therefore if it's got a longer wavelength, that must be a redder, because red has a longer wavelength, the blue has a shorter wavelength, so therefore you can work out what colours that they should be as well. The next question says, Table 1 summarises some of the properties of 4 stars in the constellation Hercules. Firstly, define the parsec. You may wish to use a diagram as part of your answer. Then deduce which star is larger, Copernicus or Reticulus. One of the 4 stars has the peak in its blackbody radiation curve at a wavelength of 1 micrometer. Calculate the corresponding temperature for this curve. Explain which star produced the blackbody radiation curve described in question 1.3. Then which star has the brightest absolute magnitude, and then determine the absolute magnitude of Sarin. So pause the video now, then unpause the video when you want to go through your answer. Right, as I said before, you can define the parsec as it's the distance at which 1 AU will subtend an angle of 1 arcsecond, which is 1/3600th of a degree, or you could draw that right angle triangle with 1 AU with 1 parsec and 1 arcsecond on your diagram. Now, which star is larger? Well, you look at that, you can work this out from using Stefan's law, because we know we've got A in that particular equation. Now you'll see that both of them are in the same spectral class. Now we assume that when things are in the same spectral class, they have the same surface temperature. So therefore, they have the same apparent magnitude, but Copernicus is significantly further away. So you can see that from the information given to us. So therefore, it will have the higher power output, so therefore it'll have the brighter absolute magnitude. So to have the greater power output at the same temperature, it must have a greater area, so it must be bigger. Now the next one, again, we've got to use our equation for the Wien displacement law of lambda max times by t equals 2.9 times 10 to the minus 3 to work out our value. Now think about which star will produce that. Well, this comes from you being able to link the temperatures to the spectral classes, and you've got to memorize what those values are, and that is it must be in spectral class M if it has that particular surface temperature. So therefore the only one that's M is Rastelecki. Now, which star's got the brightest absolute magnitude? Again, it's Rastelecki. Now, how you can think that one through is, look, it's a significantly further distance away compared to all the other stars. However, all the other stars have a very similar apparent magnitude of brightness on the Earth, so therefore it must be the brightest because it's the furthest away, yet they all appear as similar brightness on the perspective of the Earth. And then the last one, you can work out this absolute magnitude by using your equation. M minus M equals 5 log d over 10. Luckily, in the question d is given in parsecs, no need to convert. Pop in all the values and we get 1.3. The next question says, the table summarises some of the properties of 2 stars in the constellation Ursa Minor. Using these data, describe and explain one similarity and one difference in the appearance of the 2 stars as seen with the unaided eye by an observer on the Earth. Then deduce which of the 2 stars is further from the Earth. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you can think about firstly the brightness, and you can also think about the colour. So the first thing you can work out is the brightness is the apparent magnitude. So straight away, because they've got the same apparent magnitude, they'll appear the same brightness from the Earth. But the difference is going to be linked to their colour, which is linked to their spectral class. So you should hopefully know the differences by learning the colours of the spectral classes. So Cohort, because it's a class K, would appear orange or red. Polaris, because it's a spectral class F, would appear yellow or white. Now, how can you work out which star is further away? Well, again, you're given the radius of the star, and then you can work it through by the Stefan's law by doing P equals sigma AT to the 4. Now, both have the same area, but we can say that because Polaris is in spectral class F, we should know that has a higher surface temperature than K. That's just a fact you've got to learn. So therefore, it must have a higher power. So therefore, Polaris must have a greater power output, but they both appear the same brightness from the perspective of us on Earth. So therefore, Polaris must be further away from the Earth, so it doesn't appear as brighter than Cohort. Next question says, the summer triangle consists of 3 stars, Altair, Deneb and Vega. Some of the properties of the 3 stars are summarised in the table on the screen. The 3 stars belong to the same spectral class. State and explain which spectral class they belong to. Deduce which of the 3 stars appears the brightest, and calculate the distance from the Earth to the closest of the 3 stars. So pause the video now. Then unpause the video when you want to go through your answer. Right, in this first one, you've got to learn the temperatures and how they're linked to spectral classes. So it's spectral class A because that's the temperature range they all go into. Which will appear the brightest? Well, that's the one with the most negative apparent magnitude. So therefore it's Vega from the values given. And then the distance to the closest of the stars, well, you should work out that, that Altair is going to be the closest of the 3 stars. You can tell that because if you look at its absolute magnitude compared to its apparent magnitude, well, that's got quite a bright apparent magnitude perspective from the Earth compared to its absolute magnitude. Now you can see Deneb is very bright from 10 parsecs away, but from where it is on Earth it's much dimmer, so therefore it must be really far away. And then Vega has approximately the same apparent and absolute magnitude, so therefore it must be about 10 parsecs away. But Altair, because it's a lot brighter from the perspective of Earth compared to what it actually is 10 parsecs away, must be a lot closer to us than 10 parsecs, so it has to be Altair that's the closest. Pop in all the values, work it through, and you get 5.2 parsecs. Now, from this information again, deduce which of the 3 stars is the largest, and then calculate the wavelength of the peak in the blackbody radiation curve of Altair. So pause the video now, then unpause the video when you want to go through your answer. Right, so how can you work it through? Well, again, we're looking at area, so we've got to use Stefan's law again. So the answer is Deneb, because they all have approximately the same temperature, because they're all in the same spectral class. We're going to assume the temperature is constant. So therefore, okay, Deneb, okay, has the highest absolute magnitude from the information given to us, so therefore has the highest power output. So therefore, it must have a much greater power output, so therefore it must be the largest of the stars. So therefore P equals sigma AT to the 4, because T is constant, the only factor affecting P is A, so therefore if the P is the highest, A is the highest. Next one, once again, we're using the Vine displacement law. Lambda max times by T equals 2.9 times 10 to the minus 3. We worked out to be 3.8 times 10 to the minus 7 meters. The next question says, during the life cycle, stars go through a number of stages. Betelgeuse is a red giant star with a luminosity of 4.49 times 10 to 31 watts. The peak intensity of the radiation from Betelgeuse occurs at a wavelength of 850 nanometers. A website claims that the radius of Betelgeuse is 1,000 times the radius of the Sun. Assess the accuracy of the claim. The Hertzsprung diagram shows the position of some of the main sequence stars. Add the approximate positions of the Sun and Betelgeuse to the diagram. Mark the position with label crosses, and then state what is meant by a main sequence star. So pause the video now, then unpause the video when you want to go through your answer. Right, for this first one, what we're going to do is work out the temperature of Betelgeuse, and we can do that because we've got the peak wavelength. So we can use the Vine displacement law to work out the temperature of Betelgeuse. Then what we can do is we can work out the luminosity of both Betelgeuse and of the Sun. Well, it says here that we think that we can work it through. So we've got the luminosity of the Sun from the question. We can then work out the luminosity of Betelgeuse as well, and we can then equate the two of them, and then we can actually ratio the two values and work out the ratio of RB to RS from those values as shown on the screen. And when you ratio those two values, they're 991. That doesn't equal 1,000, so the claim is actually inaccurate. The next one, you've got to be aware where the stars go in the Hertzsprung diagram. The Sun, we know, has an approximate surface temperature of 5,800 Kelvin and belongs in the main sequence, so you can pop it in the main sequence part at that particular temperature, whilst we know Betelgeuse is a red giant, so must go in the red giant sector of this particular diagram. And then a main sequence star, by definition, is a star which is carrying out hydrogen fusion in its core. The next question says, Table 1 summarizes some of the information about 4 stars in the constellation of Cassiopeia. State which star in Table 1 is the dimmest on the absolute magnitude scale. Calculate the absolute magnitude of Shadar. Then Chush has a mass over 15 times the mass of the Sun. Chush must eventually collapse to form a black hole. Calculate the radius of the event horizon for a black hole with a mass 15 times that of the Sun. So pause the video now, then unpause the video when you want to go through your answer. Right, the dimmest one is going to be the one with the highest absolute magnitude, and you can work that through because they've all got approximately the same apparent magnitude, the same brightness, okay, from from the Earth. However, they've all got different distances. So Kapf, because it's the closest to us, okay, but they all appear the same brightness from the Earth, okay, must be the dimmest, and Ch must be the brightest because it's the furthest distance away. You can work out the absolute magnitude by doing the equation m minus m equals 5 log d over 10. Remember, d has to be in parsecs, not light years, so convert that, okay, and then you work it through to be minus 2. Then this next one, we've got to use a Schwarzschild radius, so RS equals 2gm over c squared. Pop in all the values. Remember, it's over 15 times the mass of the Sun. The mass of the Sun is given to you on the equation sheet, so you get 4.4 times 10 to the 4 meters. The next question says, Table 2 gives some data about the supergiant star Melnik 34 and the Sun. Calculate the power output of Melnik 34 divided by the power output of the Sun, that ratio. Then discuss why the evolution of a supergiant star in a local part of our galaxy could be dangerous for life on Earth. So pause the video now, then unpause the video when you want to go through your answers. Right, so in this first one, we need to work out the power output of each one. We're given the temperature, we're given the radius, we've got to use Stefan's law. Now remember, we can work out the area by doing 4 pi r squared for each one. So you can work out each one, ratio the two, and you get 3 times 10 to the 6. Now the next one, why could they be dangerous for life? Well, it's because when a star undergoes a supernova collapse and it forms a neutron star or black hole, it'll produce a gamma ray burst. Now the gamma ray burst can destroy the ozone layer of a planet such as the Earth, which would then be dangerous for life on Earth. The next question says, using the axis below, sketch the emissive power of a black body as a function of the wavelength for 3 temperatures, 1000 Kelvin, 1200 Kelvin and 1600 Kelvin. Indicate the temperatures on each curve. Vine displacement law can be written as lambda max times by t equals a constant. What does lambda max represent? Then obtain the value of the constant from the data booklet, 2.9 times 10 to the minus 3, and calculate lambda max for a temperature of 1600 Kelvin. And then assuming that lambda max for the Sun lies within the range of the visible spectrum, use the Vine's law to estimate the temperature of the Sun. So pause the video now, then unpause the video when you want to go through your answer. Right, this question firstly is testing your ability to remember a black body radiation curve. Now remember, for a black body radiation curve, the higher the temperature, the higher the curve will be for all parts of the line, but it will also have its peak shifted to the left hand side. So as you can see here, as the temperature increases, the peak shifts to the left, but the value for all of them increases as well. Now lambda max represents the peak wavelength of intensity, so it's not the highest possible wavelength of emission, rather it's the wavelength at which you get the highest intensity of radiation. Now the next one, we do lambda max times by t equals 2.9 times 10 to the minus 3, pop in all the values and we get lambda max to be 1800 nanometers. Now for this next one, you've got to assume that approximately the wavelength of visible light is about 550 nanometers. Pop it into the equation and we get about 5300 Kelvin. So that brings an end to our revision session in today's lesson. So hopefully, if you've learned in this particular revision session, and you can hopefully answer A-level physics examination style questions, you can assess your understanding on AQA A-Level Physics and understand what topics you need to improve upon for AQA A-Level Physics. So thank you very much for carrying out this particular revision session on the Astrophysics module for paper 3 of AQA A-Level Physics on the module of stars. Thank you very much and have a lovely day. Have a look at some questions for cosmology. The first question says a particular line in the spectrum of light from a source in a lab has a frequency of 6.173 times 10 to 14 Hz. The same line in the spectrum of light from a distant galaxy has a frequency of 6.142 times 10 to 14 Hz. Deduce what can be concluded about the distant galaxy, and you should include a calculation. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question, you've got a frequency and you've got the lab frequency, so you should use the Doppler effect equation, which is the change in frequency over the frequency equals V over C. The change in frequency is the difference between the two frequencies. F is the frequency of the lab. You pop in all the values, you get minus 1.51 times 10 to 6 meters per second, so therefore it tells you the galaxy is receding away from the Earth. The next question says a police siren is observed to change pitch as it passes a stationary observer. Explain this observation. Then explain why the driver of a race car does not experience any Doppler shift in the sounds from the engine. Light from a distant galaxy is redshifted. Suggest how by measuring the redshift of different parts of the galaxy, astronomers are able to determine the speed of rotation formation of the galaxy, then suggests why the light reflecting off a sprinter running towards a TV camera does not appear to be blue shifted. So pause the video now, then unpause the video when you want to go through your answer. Right, this links to the Doppler effect and all the observations that come from it. Now, the first one is when the car is moving towards the receiver, the space between the observer and the emitter is compressed, so therefore the sound wave is compressed. So therefore there are more waves per second, so it's pitched higher. When the car is moving away from the receiver, there's more space for the sound waves to go into, so the sound waves become stretched. There is a lower frequency, so therefore the sound is lower pitched. Now, for the second question, remember it's all about relative motion. So there's no relative motion between the driver and the source, so therefore the waves received will not be Doppler shifted. You'll have the same wavelength and the same frequency as when it was emitted. Now, in the third question, as a galaxy is redshifted and it's rotating around, okay, each side of the rotating galaxy will have a different velocity and therefore a different redshift. The side rotating away from us will have a greater velocity and a greater redshift. The side rotating towards us will have a lower velocity and a lower redshift. The difference in the two relative velocities can then give the difference in the wavelengths, which can therefore lead to the velocity of the rotation being calculated. And in the last question, remember that the speed of the runner is a lot less than the speed of light, so therefore any change in wavelength of the reflected wave will be extremely small, so therefore the human eye will not detect it. The next question says, a particular absorption line is measured in a lab at a frequency of 5.12 times 10 to 14 Hz. Calculate the frequency and wavelength associated with the same line in a galaxy moving away from the Earth at 10.6 megameters per second, a galaxy moving away from us at 25% of the speed of light, and then an absorption line is measured in the lab of a wavelength of 714.7 nanometers. In a distant galaxy, the same absorption line is observed with 707.1 nanometers. Calculate the speed of the galaxy and state whether it's moving towards or away from the Earth. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you should again use the Doppler effect equation. The change in frequency over the frequency is equal to the speed over the speed of light. We can work out what our change in frequency is because we have all the other values. We can then work out the change in frequency is 0.180 times 10 to 14 Hz. So therefore our observed frequency is going to be the value of the lab minus that number, because we know it's moving away from us, so the frequency therefore must be decreasing. We've then got our new frequency. We can say wavelength of speed over frequency, therefore 608 nanometers. Same idea for the next one, however this time we're going to be using 25% of the speed of light as our value for V, so it's 25% of 3 times 10 to the 8, work it all through and we get our wavelength to be 782 nanometers. Now in this last one, because we've got wavelength and we've not got frequency, we've got to use the wavelength aspect of the equation, which is the change in wavelength over wavelength equals V over C. So the change in wavelength, you can see from the information given, is the difference, so it's 7.6 nanometers. So if we can work out V and we get 3.19 times 10 to the 6 meters per second. Now we know, because the frequency, which is the wavelength that is being observed, is actually got shorter, so it tells us it must be blue shifting and the galaxy is moving towards the Earth. The next question says, state two pieces of evidence in support of the Big Bang Theory. Explain the importance of the discovery of the cosmic microwave background radiation. Then, if the universe is between 11 and 15 billion years old, calculate the maximum and minimum possible values for the Hubble constant seconds to the -1. Estimate the peak wavelength of electromagnetic radiation in the universe when its temperature is 10 to the 11 Kelvin. And then estimate the temperature of the universe when it was full of visible light. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, there were three bits of evidence for the Big Bang Theory: the redshift of the universe, the cosmic microwave background radiation, and the relative abundance of hydrogen helium, 25 to 75%, in deep space. Now the CMBR, the cosmic microwave background radiation, is very important because it was predicted by only the Big Bang Theory. No other theory of the origin of the universe could explain the CMBR, so it allowed the Big Bang Theory to be accepted. Now the Hubble constant is 1 over the time of the universe. Now we've got to do that in seconds to get our Hubble constant seconds to -1, so we convert 11 billion and 15 billion years into seconds. We then pop them in and we get our two answers: 2.89 times 10 to -18 seconds to -1 and 2.11 times 10 to -18 seconds to -1. Now the next question, we assume the universe is a black body radiator, so we use the Wien displacement law, which is the idea that lambda max is equal to 2.9 times 10 to the minus 3, over the absolute temperature. So you pop that all through and we get 3.0 times 10 to the minus 14 meters. In the next question, we can still use the Wien displacement law and consider the universe as a black body radiator, but this time we know our wavelength, so we can estimate the wavelength of visible light to be about 500 nanometers. That's a value you should know. Pop it into the Wien displacement law equation and we get 6000 Kelvin as our answer. The next question says, state 3 pieces of evidence in support of the Big Bang theory. Describe why it is not possible for atoms to form until 380,000 years after the Big Bang, and then describe the observations that led to the development of the idea of dark energy. So pause the video now, then unpause the video when you want to go through your answer. As we said before, 3 bits of evidence are the redshift of the universe, the microwave background radiation found in all directions, and the relative abundance of hydrogen and helium in deep space due to the early fusion that took place in the universe. The next question is important to understand that until 380,000 years after the Big Bang, the universe was too hot. That meant the atoms were ionized, and eventually the universe cooled down enough for the nuclei to hold onto their electrons and form atoms. Now, how do we develop the idea of dark energy? Was when we observed distant galaxies, we observed that they were accelerating away from us, indicating that the expansion of the universe was happening at an increasing rate. It was accelerating. So for this acceleration to happen, a source of energy was needed, which we consider to be dark energy. The next question says, the universe originated from a Big Bang. The table shows how the temperature of the universe has changed with the time since the Big Bang. Plot a graph of the log of the time against the log of the temperature. Time and temperature are related by the equation. Temperature to the power n times by time is equal to a constant, where n is an integer. So use a graph to determine the value of this for n. So pause the video now, then unpause the video when you want to go through your answer. Right, for this type of question, you've got to remember a log against log graph will give you a straight line, as you can see here, and you can see that in this straight line graph, from the rules of logs, that the gradient of the line will be equal to this value of n, because you know that when you plot your log against log graph, the gradient of the line of best fit that will be produced is the power to which the x-axis value is given to. So therefore, to work out n, which is the power given for temperature, you can draw the graph, you work out your gradient, it's equal to 2, so therefore n equals 2. The next question says, a line in a spectrum emitted by a galaxy is shifted from 402.5 nanometers, the lab standard, to 403.4 nanometers. Calculate the recession velocity of the galaxy in kilometers per second. Describe 2 of the pieces of evidence that the universe is expanding. Before the launch of the Hubble Space Telescope, the estimates of the Hubble constant were subjected to errors of 50%. Measurements made by the HST mean that the accuracy now estimated to be plus or minus 10%. Suggests why this is. Then the HST has imaged the most distant quasar, which has a redshift of 7.54. This redshift predicts an age of the universe of 13.8 billion years. Deduce the distance to the galaxy in an appropriate units. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we use our redshift equation. We've got our wavelength, so it's going to be the change in wavelength over the wavelength equals minus v over c. Rearrange that, make v the subject. We can work out our change in wavelength from the information given. Now remember, we want our value in meters per second, so therefore you've got to convert your nanometers into meters. So you pop in all the values and you get 670 times 10 to the 3 meters per second, which is 670 kilometers per second. Now the other bits of evidence for expansion, the universe expanding, is the Big Bang theory evidence. So therefore it is the cosmic microwave background radiation, and then the hydrogen helium abundance, which is accounted for by the brief period of fusion in the early universe. Now why is there a less on values? Because the resolution of the measuring device of the HST have improved, so the measurements of the velocity and the distance can be made with much more precision and accuracy, and the radiation absorbed by detectors in the HST has not been scattered by the atmosphere as an Earth-based telescope would have, so there is less spread in the values. Now the next one, we know our Hubble constant is 1 over the age of the universe, which we can link into because we know that D is equal to V times by the age of the universe. We can pop in all the values, work it all through, and we get 341 light years. The next question says, a supermassive black hole has a mass equal to 500 million solar masses. Calculate the Schwarzschild radius of the black hole. Compare the density of the black hole with the density of the Sun. Explain why the Sun will not become a black hole. Then a supermassive black hole can form a quasar. A quasar in the constellation Lynx has a power of 10 to the 42 watts. The Sun has a power of 4 times 10 to the 26 watts. Calculate how close to the Earth the Sun would have to be to appear to have the same power as the quasar. And then some quasars are too distant to be imaged by a single radio telescope. Explain why. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we've got our mass in solar masses. So you can find out the mass of a solar mass by using the equation sheet. So you can work it through by doing 5 times 10 to the 6 times by 1.99 times 10 to the 30 to get your mass of the black hole. We then use the Schwarzschild radius equation 2gm over c squared to work out our value to be 1.5 times 10 to the 10 meters. Now we can work out density for both the objects, which we assume both of them are spherical. So we can say density is mass over volume, where volume is 4 over 3 pi r cubed. Now you've got the density, you've got the radius of the black hole in the equation. We've got the radius of the Sun on the equation sheet, so we can work out both of the values for the volume from that. You've also got the mass of the Sun on the equation sheet. So you work them through and you can work out that the density of the black hole is 7.04 times 10 to the 5 kilograms per meter cubed. The density of the Sun is 1,400 kilograms per meter cubed. So therefore the density of the Sun is 500 times smaller than the density of the black hole. So the Sun has insufficient mass to produce an escape velocity that exceeds that of light, which would therefore is needed to be a black hole. In the next question, we've got to use the inverse square law, which is that P is equal to the proportional, to 1 over d squared. So we can say the power of the quasar over the power of the black hole is going to be equal to the distance to the Sun divided by the distance to the quasar, because we're going P is proportional to 1 over d squared. So therefore you pop in all your values, you work it all through, and you get your new value for d to be 3,000 meters. Now the issue why it can't be imaged by one single radio telescope is that the angle subtended by the quasar at the Earth is too small to be detected by a telescope with a dish of that size at this time. So we've got to be using larger telescopes or telescopes in space to image quasars. In the next question, it says, what is the redshift of a galaxy with a recession speed of 2.2 times 10 to the 6 meters per second? What about 10% the speed of light? What is the recession speed of a galaxy if the radiation of the original wavelength, 6.5 times 10 to the minus 7 meters, undergoes a redshift of 3.7 times 10 to the minus 8 meters, and a star received at a velocity of 9.2 times 10 to 3 kilometers per second emits radiation of wavelength 410 nanometers? What is the extent of the redshift of this radiation when it's received on Earth, and what is its received wavelength? So pause the video now, then unpause the video when you want to go through your answer. Right, in this particular question, once again, it's the idea of using the Doppler shift equation. So here we have, so we want to work out redshift, so we know it's V over C. So we've got V, so we pop them in and we get 0.0073. Same idea for 10% the speed of light. So 10% the speed of light is 3 times 10 to the 7. So it's 3 times 10 to the 7 over 3 times 10 to the 8, so it's 0.10. In this next one, we have our change of wavelength. We have our original lab spec wavelength. We can then say V over C equals a change in wavelength over wavelength. So V equals change in wavelength over wavelength times by C. Pop in all the values and you get 1.7 times 10 to the 7 meters per second. Here we've got our wavelengths now. So we can work out our change in wavelength, because we can say V over C is equal to the change in wavelength over wavelength. So the change in wavelength is V over C times by wavelength. We get 1.26 times 10 to the minus 8 meters. Now because we know that it's redshifting, therefore the wavelength must be longer. So therefore the observed wavelength is the lab standard wavelength plus this change in wavelength, so it's 422 times 10 to the minus 9 meters, or 422 nanometers. The next question says GNZ11 is one of the most distant observed galaxies in the universe. A redshift Z of 10.96 has been detected by the Hubble Space Telescope for radiation from this galaxy. Radiation with a wavelength of 134 nanometers was emitted from GNZ11. Calculate the wavelength of this radiation when it's detected at the Hubble Space Telescope. The graph shows how Z for emitted light from a galaxy varies with the distance that the light has travelled in reaching the Earth. A light year is the distance travelled by light in 1 year. Determine the distance light from GNZ11 has travelled in reaching the Earth in meters. Then the recently launched James Webb Space Telescope is designed to operate in the infrared region of the spectrum. Explain how this will be helpful for studying distant galaxies from the Earth. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, we again can use our redshift equation. So we know that z is equal to the change in wavelength over the wavelength, okay, times by so we know z is 10.96. So therefore, we can work out what our original wavelength is by working out what the difference is, divided by the lab standard, and then look at it equal to 10.96. So if you work it all through, you can get it equal to be 1.60 times 10 to the minus 6 meters. In this next question, we know that the distance that is travelled, as you can see from our diagram, tells us that it's going to be at 13.4 times 10 to the 9 light years by looking at the graph. We can then convert the light year into meters by using our conversion factor, 3.15 times 10 to 7 seconds. We can therefore say that the distance is going to be speed times by the time, so you can work it through like so. So you get it out and you get it to be 1.26 times 10 to 26 meters. Now the next question says, why are we useful for distant galaxies? Well, we know that very distant galaxies have a very large redshift. So therefore, if they've got a very large redshift, it'll be so redshifted that the wavelength is so great that the visible light becomes infrared when it arrives at the Earth. The next question says, U Cephei is an eclipsing binary system consisting of two stars that orbit their common centre of mass. The primary star is class B and the secondary star is class G. Figure 1 shows the variation of the apparent magnitude of U Cephei with the time as observed from Earth. Firstly, explain the shape of the graph in figure 1. Then a particular spectral line has a wavelength of 486.136 nanometers when measured from a source in the lab. The line is also present in the absorption spectrum of the primary star of U Cephei. When observed from the Earth, the wavelength of the primary star's absorption line varies as shown in Table 1. State why the average of the values in Table 1 is different from the lab value. Then show that the orbital speed of the primary star is about 250 kilometers per second. Calculate the orbital rate of the primary star. Then a different eclipsing binary star system is thought to consist of a white dwarf and a neutron star. Discuss how astronomers could confirm this. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, why are we getting these dips? So the minima in these graphs are caused when one star passes in front of the other. The deeper minima is caused by the cooler star passing in front of the hotter star, because there'll be a greater dip because we've got most of the hotter star blocked out when the cooler star is in front of it. In this next question, we can say that y is the average different from the lab value. So the system is moving towards us, so you've got the redshift. So therefore, the system is also moving, so therefore our light is going to be blue shifted. So the value is not going to be the same as the average. Now in 1.3, you've got your minimum and maximum value. So therefore, the change in wavelength, as you can see from the previous question, you're given the maximum, you're given the minimum. So therefore, our change is therefore going to be equal to 0.413 nanometers. We know Z is the change in wavelength over the wavelength, so you get that to be 8.50 times 10 to the minus 4. Now in this case, because we don't have a lab standard for the wavelength, it is the average of the two values. We can therefore say V is equal to Z times by C. We've got our value for Z from the previous question. We can multiply it by C, which ought to be the 3 times 10 to the 8. So we get 2.55 times 10 to 5 meters per second, or 255 kilometers per second. Now we can see from the actual graph given before that the time period is 2.5 days, because that's the time it takes for one complete cycle to occur. We know that from the gravitational field unit that V is equal to 2 pi r over t. It's just going to be the circumference over the time for the velocity. So therefore r is equal to Vt over 2 pi. Pop in all the numbers. Remember to turn our time from days into seconds, and we get 8.76 times 10 to the 9 meters. And then how do we ever confirm any binary star system? Well, it comes from the fact that you've got to think about one of the objects blocking out the other. So the neutron star will emit radio waves. So the radio emissions from the neutron star, which is a fact that we know, will be blocked by the white dwarf star when they pass in front of it, so you can detect its presence. The next question says, a particular spectral line in the spectrum of a star is found to have a wavelength of 600.80 nanometers compared to 600.00 nanometers as measured in the lab. What is the velocity of the star? Is it moving towards or away from us? The H-alpha spectral line in the hydrogen spectrum is 656.00 nanometers when measured in the lab. Star A is observed to have that line at 656.60 nanometers, star B at 655.90 nanometers, and star C at 656.40 8.40 nanometers. Which star is moving the fastest relative to the Earth? What is the direction of motion of each of the stars? Their neutral atomic hydrogen gas in the spiral arms of the Milky Way emits a spectral line of wavelength 21 centimeters, which is in the microwave part of the electromagnetic spectrum. The spectral line, when detected by a radio telescope in a certain orientation, is observed to be shifted by 0.1 mm less than 21 centimeters. How fast is this part of the galaxy moving relative along the line of sight? Is it moving towards us or away from us? So pause the video now, then unpause the video when you want to go through your answer. So, to answer this question, you've got to consider again using the Doppler shift equation. So we know that we can work out in this first question our change in lambda by doing the apparent lambda minus the lab spec lambda. We can then say V equals a change in lambda over lambda times by C, work it through, and we get minus 4 times 10 to the 5 meters per second. Now, because V is a negative, it shows that the star is receding away from the Earth. Now, in the next question, once again, we work out the change in the wavelength, because the change in the wavelength will tell us how fast they will be moving away from us, because they'll all have the same lab spec for their wavelength. So if you work out their change in wavelength, that will then give you the value that you require. So if you work it through, you can see that star A has the greatest shift, the greatest change in wavelength, so therefore must be moving the fastest relative to the Earth. And because if you can see here in star A we've got a positive, and star C we've got a positive, but then star B we've got a negative, it tells us that A and C are receding from the Earth. A negative velocity will tell us that we're receding, while star B must be blue shifting, must be coming towards us. Once again, in the third question, we work out our change in wavelength by working it through to be minus 1 times 10 to the minus 4 meters. We know V over C equals the change in wavelength over the wavelength. Pop it all through and we get 1.4 times 10 to the 5 meters per second. Because the value is a positive, it will be moving towards us. The next question says, measurements of the shift in the 21 centimeter H1 line in the spectrum of the galaxy M84 suggest that it's receded at a velocity of 900 kilometers per second. Calculate the value of redshift for this galaxy and calculate the distance to this galaxy. So pause the video now, then unpause the video when you want to go through your answer. Right, in the first one, what we're trying to do is trying to work out Z, the redshift. So we say Z is equal to V over C. We know what V is, but remember, for this equation to work, they've got to be in the same units. So therefore, we've got to place 900 kilometers per second into 900 times 10 to the 3 meters per second. So we get Z to be 3 times 10 to the minus 3. We can then work out the distance, because we know that distance is equal to the recession velocity divided by the Hubble constant. Now the Hubble constant is given to be 65, but when we use this equation, we can then have to make sure that the velocity is in kilometers per second. So we then turn it back into 900 to get 13.8 megaparsecs. In the next question, it says Kruger 60 is a binary star system quite close to the Sun. The wavelength at which the intensity of radiation is at a maximum is 850 nanometers for Kruger A and 1500 nanometers for Kruger B. A website states that the surface temperature of Kruger A is double the surface temperature of Kruger B. Assess whether the website statement is accurate. Kruger B can be used as a standard candle. Describe how standard candles can be used to determine the distance to galaxies. Then NGC 1357 is a spiral galaxy moving away from the Milky Way at a speed of 2.02 times 10 to the 6 meters per second. The spiral galaxy is 8.7 times 10 to the 23 meters from the Earth. Calculate a value for the age of the universe in years. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we're looking at using the equation which for Stefan's law to link our temperature and wavelength together. Sorry, not Stefan's law, it will be the Vine displacement law. Now what we can say is, because we know that temperature and wavelength are linked by a constant, we can just ratio the two. So we can say T, like the temperature of A over the temperature of B, is equal to the wavelength of B divided by the wavelength of A. Now remember, because they're linked as inverse proportionality, that's why we've got them flipped on the other side. So you work it through and it's 1.76 is the ratio, so the surface temperature is not exactly double. Now you've got to be aware of the definition for a standard candle. So standard candles are stellar objects with a known absolute magnitude. So you locate a standard candle in your galaxy, you would measure the apparent magnitude, you would then use the equation of small m minus big M equals 5 log d over 10 to then calculate our distance, because we would know the absolute magnitude, we would know capital M, so we can then work out what d is in the equation. In the next question, we know that Hubble's constant is the recession velocity divided by the distance. Now, because we've got it in meters per second in meters, that gives us our Hubble constant seconds to the minus 1. So that says that when we say t is equal to 1 over the Hubble constant, it'll give us an age of the universe in seconds. So we get 4.31 times 10 to the 17 seconds. We then convert that into years, which is 1.37 times 10 to the 10 years. The next question says Ursa Minor contains the galaxy NGC 6251. Measurements indicate that the light from the galaxy has a redshift of 0.025 and that the galaxy is 340 million light years from the Earth. Use this data to calculate a value for the Hubble constant, and then use the answer to the previous question to estimate the value for the age of the universe. State an appropriate unit for your answer. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you work this through? Well, we know V is equal to the Hubble constant times by the distance. So if we work it through with the information given to us, we can therefore actually say that V is also going to be equal to the values working it through to be V times by C. So therefore V is going to be 7.5 times 10 to the 3 kilometers per second. You'll see here we've used C as 3 times 10 to the 5 because we need for our Hubble's constant equation for V to be in kilometers per second or meters per second. We need to also have our distance in megaparsecs. So we change 340 million light years into megaparsecs by dividing 340 by the conversion factor to megaparsecs, which is 3.26. So we get 104 megaparsecs. So we do 7.5 times 10 to the 3 over 104, so we get 72 kilometers per second per megaparsec. Now the age of the universe, as we said before, is 1 over the Hubble constant. Now to work this through, you need to get your value in seconds, so you've got to convert your Hubble constant you've just previously worked out to go from kilometers per second per megaparsec into seconds to the minus 1. So when you do that and work it through, it's 4.3 times 10 to the 17 seconds. The next question says, show that the reciprocal of the Hubble constant as the unit of the second, then the radial velocity of the Coma cluster of galaxies being measured at 7,200 kilometers per second. What is the distance to the cluster? Then the graph shown below has the recession velocity against the distance for a number of galaxies. Estimate from it the value of the Hubble constant. And then what is the distance in megaparsecs of a galaxy with a z of 0.002? So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, we know that V is equal to H times by D. So 1 over H is D over V. So we could say, if we, for example, say that distance is in kilometers and velocity is in kilometers per second, the kilometers cancel through, so our units are seconds, because 1 over seconds to the minus 1 is seconds. In the next question, we say V equals H times by D. Now we want to work out our distance in megaparsecs, so therefore we have our velocity in kilometers per second, and we have our Hubble's constant in kilometers per second per megaparsec. We work it through, and we get 107 megaparsecs. Now in the next question, you'll see that you've got the recession velocity on the y and the distance on the x, so therefore the Hubble constant will be the gradient of your line. So it's about 203 was the change in y divided by 3, the change in x, so we get 68 kilometers per second per megaparsec. Now we know in this next one that the V is equal to Z times by C. Now when you work this through with your Hubble constant in kilometers per second per megaparsec and Z as in just a number, so it's 0.002, well then we get our velocity in kilometers per second, therefore distance is velocity over the Hubble constant, so we get 8.8 megaparsecs. The next question says there's some uncertainty in the value of H, 71 plus or minus 10% of kilometers per second per megaparsec. If the galaxy is moving away from us with a recession velocity of 5,500 kilometers per second, calculate its maximum and minimum distance from us. And how is the estimated age of the universe affected by this range of value for H? And then suppose that the universe stopped expanding and started contracting. What feature in the spectrum of the galaxies would now enable us to tell us that this had happened? So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, well, we can work out the 10% of 71, so 10% above is 78 and 10% below is 64. Then what we can do is then use this to work out distance. Distance is going to be velocity over Hubble's constant. It'll give us our distance in megaparsecs, so we've got a maximum to be 86 megaparsecs, because remember the smallest Hubble constant will give us the biggest distance because of how the equation is, and then the minimum distance is 71 megaparsecs. Now for the estimated age for each one, you've got to convert the Hubble constant from kilometers per second per megaparsec into seconds to the minus 1. But as you can see there, you would do that by dividing by 3.1 times 10 to the 19. So you work that through and you get 5 times 10 to the 17 seconds, which is 15.9 billion years, and 4 times 10 to the 17 seconds, which is 12.7 billion years. Now you can observe if the universe was contracting because we would observe blue shift in spectral characteristics from distant objects because it indicates coming back towards us. The next question says, the following statement appears on a website. Messier 87 is 55 million light years from the Earth. The spectrum of the light from M87 includes an absorption line at a wavelength of 394.5 nanometers. The same line is produced by a source on Earth with a wavelength of 393.4 nanometers. A light year is the distance travelled in a year by light in a vacuum. Assess the accuracy of the statement made on the website. So pause the video now, then unpause the video and you want to go through your answer. Right, in this one, what you need to do is you need to work out what the velocity of the object is travelling as receding from the Earth at. So we can say that v is equal to the change in wavelength over the wavelength of the lab standard times by c, which is 3 times 10 to the 8. So you work it all through and you get your value to be 8.39 times 10 to the 5 meters per second. Now we can then use the Hubble's constant equation, which says d equals v over the Hubble's constant. But remember, for this to work, we really need to either have the Hubble's constant in seconds to the minus 1, or you'll have to have your distance in you'd have to get your velocity in kilometers per second and your Hubble's constant in kilometers per second per megaparsec, and we get our distance out in megaparsecs. But in here, we've got our Hubble's constant is in seconds to the minus 1, so the distance is 5.18 times 10 to the 23 meters. So therefore, what we can do is we can work that out to be 5.48 times 10 to 7 light years. So it tells us that the statement is going to be correct. The next question says, the cosmological microwave background has a thermal blackbody spectrum at a temperature of 2.725 Kelvin. What is the peak emission wavelength, and how does this explain the name of the background radiation? Then explain how the observed abundances of hydrogen and helium are seen as evidence for the Big Bang. Then the early universe contained only light elements. However, at the present time, there are large amounts of heavier elements. Explain this. And then the Big Bang theory postulates that as the universe cooled after the Big Bang, there were 7 protons created for every neutron, so that this predicts that the helium abundance by mass in the early universe was 25%. So pause the video now, then unpause the video and you want to go through your answer. Right, so for this one, you've got to treat the universe as a black body radiator. So we use divine displacement law. Lambda max is 2.9 times 10 to the minus 3 over the absolute temperature. So we get 1.1 millimeters, which is in the microwave region of the electromagnetic spectrum, which is why it's called a cosmic microwave background. Now in question 2.1, the Big Bang theory proposes that the primordial nucleosynthesis, which is the formation of hydrogen nuclei from free protons and neutrons, and the formation of helium nuclei from the fusion of hydrogen. The theory predicts a hydrogen to helium ratio of 3 to 1, which is very near to what we see today. And we now get heavier elements because the heavier elements are made by fusion in stars, which, when the star ends its life in a supernovae, is then dispersed in the interstellar medium. Now in the last question, the nucleus of helium has 4 nucleons made of 2 protons and 2 neutrons. So if the ratio of protons to neutrons was 7 to 1, to assemble 1 helium nucleus means you'd be needing 14 protons and 2 neutrons, of which 2 neutrons combine with the 2 protons, leaving 12 extra protons. So 4 of the original nucleons are used up in the helium nucleus and the other 12 are still protons, so they become hydrogen nuclei. So therefore you get your proportions. The next question says, a star in a distant galaxy is receding from the Earth. A physicist measures the wavelength of the hydrogen absorption line in a lab source to be 725 nanometers. The wavelength of the same absorption line in the spectrum of the star has been shifted by 35 nanometers. Calculate the star's distance from the Earth. Then, assuming h has been constant since the universe began, the universe is approximately 13.7 billion years old. Why is this figure only an estimate? And then a student claims that this means he can calculate the absolute size of the universe. Why is he wrong? So pause the video now, then unpause the video when you want to go through your answer. Right, again, in this first one, we can use the redshift equation or the Doppler shift equation. Z is equal to the change in lambda over lambda. So we work out what Z is by finding out difference and dividing it by the lab sample. So we get 0.00482. Multiply that, therefore, by C, and we're going to get our value for V out, which is 1.44 times 10 to the 7 meters per second. We can then convert that into kilometers per second to use then in the Hubble's constant equation. So D equals V over the Hubble's constant. Pop in the values, you get your distance out in megaparsecs. The answer is 200 megaparsecs. This value is an estimate because we actually think the Hubble constant has not been constant since the universe began. And we can't calculate the absolute size of the universe, because if the universe is 13.7 billion years old, the observable universe is limited by the time taken to travel to us. Some light will have not reached us yet, so the actual size of the universe cannot be calculated. The next question says, astronomers can detect microwave background radiation coming from space in every direction. The temperature of this microwave radiation is 2.7 Kelvin and its total intensity is about 3 times 10 to the minus 6 watts per meter squared. Describe the origin of the microwave background radiation. The figure below shows how the intensity of the microwave background variation varies with its wavelength lambda. The peak intensity is at a wavelength of 1.1 millimeters. This spectrum of the microwave background radiation changes with the temperature according to Wien's displacement law. Suggest and explain how the spectrum might have looked in the distant past. Then calculate the energy of a photon which has a wavelength of 1.1 millimeters, and then estimate the number of photons of the microwave background radiation incident per second on the back of your hand. Assume all emitted photons have the energy you've calculated previously, and the back of your hand has a surface area of 150 centimeters squared. So pause the video now, then unpause the video and you want to go through your answer. Right, so the origin of the microwave background radiation is that after the Big Bang, the universe was very hot, and the energy, the radiation, and the matter was coupled. Then the universe expanded and cooled. This decoupled matter and energy. Therefore, the wavelength of the gamma photons was subsequently increased, and therefore it was released. Now we know in this next one that lambda max is proportional to 1 over t, is the Wien displacement law. So therefore, as t is decreased over time, so in the past the peak was at a shorter wavelength, and so the further to the left on the graph. Now the energy of a photon, we can remember doing this, that it is E is equal to hc over lambda, so you can pop that through. So it's hc divided by the lambda, which is 1.1 times 10 to the minus 3 millimeters into meters, so you have 1.8 times 10 to the minus 22 joules. Now the number of photons per second is your 3 times 10 to the minus 6 times by 150 times 10 to the minus 4 over 1.8 times 10 to the minus 22, because we've linked in our energy to the amount of total energy that we've got in the overall area, so therefore it's 2.5 times 10 to the 14 seconds to the minus 1. The next question says, in the middle of the 20th century, there were two competing theories of the universe. In 1964, electromagnetic radiation was observed coming from all directions in space. Figure 2 shows the distribution of this radiation is observed from Earth. The graph provides evidence for one of these theories of the universe. Discuss the main features of this theory of the universe. In your answer, you should include the main predictions and evidence for the theory and a suitable calculation. So pause the video now, then unpause the video and you want to go through your answer. Right, so in this question, the first aspect is redshift. So the theory predicts that distant galaxies are all moving away from us. The further away the galaxy, the faster it moves, which links into Hubble's law, that V is proportional to D. The second aspect is the CMBR, that second bit of evidence. The theory predicts that the black body radiation is at microwave wavelengths because the temperature is 2.7 Kelvin, so the peak wavelength is about 1.1 millimeters. Now it's in all directions, indicating the universe was once in a very small or very hot, dense state, which is the Big Bang theory. The graph shows a peak in the microwave, and the general shape is the same as a black body, so we can assume the universe to be a black body emitter. The CMBR cannot be predicted by any other theory except the Big Bang theory, so it's the idea that it's leftover radiation from the Big Bang. And the third aspect is the ratio of hydrogen to helium, in the idea that the theory predicts that there should be a ratio of 75% hydrogen and 25% helium in deep space, which is what we observe in practice. The next question says, Cygnus A may be the nearest quasar yet discovered. Cygnus A has a redshift of 0.057. Calculate the distance to Cygnus A and state an appropriate unit. The first quasars were also discovered in the 1950s. What properties of quasars led to their discovery? So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, what do we know? We've got Z. So Z equals V over C. So we can say V is equal to Z times by C. So it's 0.057 times by 3 times 10 to the 8. So you get 1.71 times 10 to the 7 meters per second. We can then say V equals HD, but V needs to be in kilometers per second for this equation to work. We divide it by the Hubble's constant, and therefore we get 263 megaparsecs. And the property of quasars is that they're very strong radio sources as observed on Earth. The next question says, a quasar is found to lie at a distance of 5 times 10 to the 9 parsecs from the Earth. To have the same apparent magnitude as the quasar, the Sun would need to be placed at a distance of 3 times 10 to the 3 parsecs from the Earth. Using the inverse square law, calculate the ratio of luminosity of the quasar to that of the Sun. Then the absolute magnitude of the Milky Way has been estimated to be minus 20.5. The apparent magnitude of quasar 3C273 is 13. A distance measurement of 3C273 puts it at a distance of 749 megaparsecs. What is the absolute magnitude of 3C273? And how much brighter is 3C273 than the Milky Way? So pause the video now, then unpause the video when you want to go through your answer. Right, so if we say they've got the same apparent magnitude, they're going to appear equally as bright, so we can say that L is proportional to 1 over d squared. So you can say the luminosity of the Sun divided by the distance to the Sun squared is equal to the luminosity of the quasar divided by the distance to the quasar squared. Now we have the value of the distance to the quasar, we have the value of the luminosity, the distance from to the Sun in that point be 3 times 10 to the 3 because they're both in parsecs. That's fine. We've got the luminosity, or one find the luminosity of this quasar of the Sun. So you divide one by the other, and you get 2.8 times 10 to the 12. Now this next question, we're going to use m minus m equals 5 log d over 10. Pop in all the values, work it through. Remember, we work in parsecs, not megaparsecs, so we get 39. So the absolute magnitude is therefore going to be 13 minus 39, which is minus 26. Now, how can you work out the difference in brightness? Well, therefore, the difference in brightness is 5.5, because you can see the quasar is minus 26 and the Milky Way is minus 20.5. To work out the brightness difference, it is 2.51 to the power of the magnitude differences. That's Poisson's ratio. So it's 2.51 to the power of 5.5, which is about 160 times. The next question says, 3C273 was the first quasar to be discovered. IC1101 is one of the largest galaxies known. Table 2 shows some information about these objects. State the property of the quasar that led to its discovery. Show that the absolute magnitude x of the quasar 3C273 is about minus 27. Assume that the quasar and the galaxy are both viewed from the same distance. Explain which will be the brighter object and calculate the ratio of brightness of brighter object to the brightness of dimmer object. And then the black hole at the center of 1C1101 has a mass of 7.1 times 10 to the 11 solar masses. Calculate the average density within the event horizon of the black hole. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, what's the property? It's a very powerful, very strong radio emitter as observed on the Earth. This next one, we've got our apparent magnitude, we've got our distance, so we can say m equals small m minus 5 times by log d over 10, so it's 12.8 minus 5 log d over 10. Remember, we turn our megaparsecs into parsecs, so it's minus 26.6. In this next one, the quasar is the brighter the object because it's got a more negative apparent magnitude, and the more negative your absolute magnitude, the brighter the object. So the difference in absolute magnitudes from the two values is 3.8. So once again, we can use Poisson's ratio to find how much times brighter it is. So it's 2.51 to the power of the magnitude differences, so it's 33 times. And in this next question, we've got our mass, so we can then use that to work out the Schwarzschild radius by doing 2gm over c squared. Pop in all the values. Remember, so you've got the mass of the Sun there, so you've got to multiply the number of solar masses by the mass of the Sun, and we get it out to be 2.1 times 10 to 15 meters. We assume that the black hole is a sphere, so volume is 4 over 3 pi r cubed. You work out your volume, density is mass over volume, so it's 3.67 times 10 to minus 5 kilometers per meter cubed. Our next question says, calculate the distance to a quasar with a redshift of 0.12. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question, we've got z to be equal to 0.12. We know v equals zc, so it's going to be 3.6 times 10 to the 7 meters per second. To then convert that into the Hubble's constant equation, and it's being kilometers per second, d equals v over h, pop it all through, and we get 550 megaparsecs. The next question says, Thetis Carinae is a star with a radius 5 times that of the Sun. It has a surface temperature of 31,000 Kelvin, and astronomers suggest that an Earth-sized planet orbits Theta Carinae. Explain one difficulty with using the transit method to detect this planet, and the astronomers suggest that the Earth-sized planet receives a similar amount of power from Theta Carinae as the Earth does from the Sun. The average power output of the Sun is 3.8 times 10 to the 26 watts. Determine the orbital radius of the Earth-sized planet orbiting Theta Carinae. So pause the video now, then unpause the video when you want to go through your answer. Right, so you've got to know the difficulties with the transit method, and basically the transit method measures how much light is blocked out by a planet. If the planet is so small or the star is so big, very little light will be blocked out, so it wouldn't be noticed. The next question indicates that what's the power output of Theta Carinae? Well, we know power for a star is sigma AT to the 4. We can then know what the area is because it's a sphere. We say therefore it must have a surface area of 4 pi r squared. So you work it all through and you get 8 times 10 to the 30 watts. So therefore the ratio of the two power outputs is about 2.1 times 10 to the 4. So therefore when we look at our idea of the inverse square law, well therefore by that logic it must be 1.45 times 10 to the 2 times further away. So when you work that all through, it's about 2.2 times 10 to the 13 meters. Again, remember that we can say that approximately p is equal to the proportional to 1 over d squared, so it allows us to work out how much further it must be away. The next question says, figure 19 shows how the radial velocity variation measured with Doppler spectroscopy of a star being orbited by a single imaginary exoplanet moving in a circular orbit. What is the maximum variation in the radial velocity? Where is the centre of mass of the planet-star system likely to be? What is the orbital period of the planet? Then estimate the radius of the orbit of the star's wobble. With reference to the orbital period of the planet suggests whether it's close to or distant from the parent star. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, look at the amplitude of the graph. The maximum variation is plus or minus 1 meter per second. The next question, where's the centre of mass likely to be? Well, the centre of mass is likely to be very close to the centre of mass of the star because the star is much more massive than that of the planet. Now, the orbital period around the star is the same as the period of time of the radial velocity of the star, which you can tell from the graph is 2 years because it's one wavelength, if you consider it to be a wave. The next question, we've got to use circular motion. So we know V equals R omega. So therefore omega is going to be 2 pi over t. So therefore R is going to be equal to Vt over 2 pi. So we can work it through to be 1.0 times 10 to the 7 meters per second. So the orbital radius of the star's wobble is going to be similar to the radius of the sun. So therefore the planet probably orbits very close to its star. So it's going to be very, very hot. The next question says, what factors make the detection of transit exoplanets very difficult? And then figure 23 shows the reduction in brightness of the exoplanet Kepler-7b as it passes in front of its parent star Kepler-7. The radius of Kepler-7 is 1.8 times the radius of the Sun. Estimate the radius of exoplanet Kepler-7b, how big is it relative to Jupiter. Then estimate the transit time of Kepler-7b across the surface of Kepler-7. And what additional information will be needed to work out the orbital period of Kepler-7b. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, the difficulty is measuring the reduction in brightness accurately, and also the infrequency of transits which go with the Earth being in the line of sight to observe this difference. Now from the graph, you can see that the reduction in brightness is about 0.0075. So we know that the radius squared of Kepler-7b over the radius squared of Kepler is going to be 0.075. You can then work it all through, look at all the information, and you get R to be 109000 kilometers. Relative to Jupiter, it's about 1.6 times larger than Jupiter. In the next one, we look at our graph and we see that the graph has dipped for about 5 hours. That's how much time must be blocking some of the light from the star. Then to work out the orbital period, you would need to know the time between successive transits, how often it repeats itself. The next question says, figure 22 shows the light curve of an exoplanet in transit across a distant star. Approximately how long does it take the exoplanet to cross the star's disk? What is the orbital period of the exoplanet? And by what percentage is the light of the parent star reduced? And what size of exoplanet does this suggest? So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you can see here that it takes to cross the star's disk. How long does it take to dip? It's about 1/5 of the day, so on the Earth that is 5 hours. Now the orbital period is the time it takes for it to repeat itself, so again looking on that, it's 2.25 days before you get the same dip again. And then the decrease in brightness is going to be 1 over 0.9930, the lowest value on the graph, divided by 1 times by 100 is 0.7%. Now whilst that seems a small number, for a planet that's actually quite a large amount. So therefore must be quite a large exoplanet, maybe in similar size to Jupiter if the star was the same size as our Sun. The next question says, the final stage of evolution for a massive star may be a rotating neutron star. One neutron star rotates with a period of 33.5 milliseconds. As the star rotates, one side of the star moves towards the Earth while the other side of the star moves away from the Earth. This causes a range of wavelengths to be received by the observer. Ultraviolet radiation of wavelength 91.2 nanometers is emitted by the star. Calculate the maximum and minimum wavelengths observed. So pause the video now, then unpause the video when you want to go through your answer. Right, so how can you work out what the angular velocity is? Well, angular velocity is 2 pi over t, so you can work it through and you get 187.6 radians per second. We know that v equals r omega, so we know what r is from the information given. It's half the diameter in meters, so we therefore get 1.992 times 10 to the 6 meters per second. We know therefore the change in wavelength over wavelength equals v over c. Now we've got v, we've got c, we know wavelength from the information given to us, we know that value, so therefore we can work it all through and we get our answer out to be the change in wavelength to be 5.84 times 10 to the minus 10. Now we don't use a lab sample here because we just use the average value emitted by the star because we don't have that lab sample, so therefore you can add the value to get the maximum wavelength, you can subtract to get the minimum wavelength, so you get 91.8 nanometers and 90.6 nanometers. The next question says, Menkalinken is an eclipsing binary star system in the constellation of Auriga. Figure 1 shows the variation in the apparent magnitude with time for Menkalinkian. Analysis of the spectrum of one of the stars shows a periodic variation in wavelength. Figure 2 shows the results for one of the spectral lines in the hydrogen-Balmer series. The wavelength for this line as measured for a source in the lab on the Earth is 656.28 nanometers. Describe the physical processes that give rise to the shape of each graph, and go on to show how the information in the graphs can be used to determine properties such as the speed and period of the Menkalinkian binary system, and you should include appropriate calculations in your answer. So pause the video now, then unpause the video when you want to go through your answer. Right, so firstly, the time period is the time from the first dip in the light curve to the third dip, which is approximately 4 days. This is one full cycle for a wavelength graph, and therefore one full cycle is approximately 4 days. When one star passes in front of the other star, the amount of light received by us on Earth changes. The brightest apparent magnitude occurs when both stars can be seen. The dips occur when one star is in front of the other, and the similarity in dips suggests that both stars have a similar temperature, similarly sized as each other. Now the variation in wavelength is due to the Doppler effect that will occur. The peaks and troughs occurs when the stars move with their greatest velocity either towards us or away from us. So the biggest change in the wavelength from the graph is the biggest value minus the smallest value, which is 0.24 nanometers. So therefore, by using the Doppler shift equation, V is going to be equal to the change in wavelength over wavelength times by C. We can then do that. Remember, we use our average value for the wavelength here, not a lab. We can use the lab value because we're given that in the question. So it's 1.1 times 10 to the 5 meters per second. So our orbital radius is therefore going to be equal to R equals V over 2 pi over T. So therefore it's 6.1 times 10 to the 9 meters. Now the next question says, in this star system, analysis of the spectrum of one of the stars shows a periodic variation in the wavelength. The distance from the Earth to Menkalinkian is 81 light years. Calculate the value of absolute magnitude of Menkalinkian when it appears the brightest. So pause the video now, then unpause the video when you want to go through your answer. Right, so we know from this we can use the equation for apparent and absolute magnitude. M minus m equals 5 log d over 10. So when you work it through, we need d to be in parsecs. So we turn 81 light years into parsecs by divided by 3.26. We can therefore say the brightest apparent magnitude is 1.897 as shown on the graph. And therefore the brightest big M is therefore going to be working through to be minus 0.082. The next question says, treated as a single source, the Andromeda Galaxy has an apparent magnitude of 3.54 and an absolute magnitude of minus 20.62. Calculate the distance to the Andromeda Galaxy. Then the Andromeda Galaxy is believed to be approaching the Milky Way at a speed of 105 kilometers per second. Calculate the wavelength of the radio wave produced by the atomic hydrogen which will be detected from a source approaching the observer at a speed of 105 kilometers per second. The wavelength of atomic hydrogen measured in the lab is 0.21121 meters. And then some astronomers believe that the Andromeda Galaxy may collide with the Milky Way in the distant future. Estimated time in seconds which would elapse before a possible impact with the Milky Way would occur. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we've got to use that equation again of apparent magnitude and absolute magnitude. Small m minus big M equals 5 log d over 10. So you can work it all through. We get d in parsecs and then 6.7 times 10 to the 5 light years. In the next one, we use our equation from the Doppler shift. So change in lambda over lambda equals v over c. So you can work out what the change in lambda is, and we get 7.4 times 10 to the minus 5. Because we know, as it says here, it's approaching us, the wavelength is lower, so therefore we subtract it from the value, so we get 0.21114 meters. In our next question, we know time is equal to distance over velocity, so we can use that equation. Now, to get our value in seconds, we're going to have our distance in meters, so we convert the distance from our value given before. Previously, you can see here, it's going to be working it through. We worked out to be 6.7 times 10 to the 5 Pascal. 10 to 5 parsecs, so therefore we've got to change that into meters by 3.08 times 10 to 16. We then divide it by the velocity in meters per second, which we know to be 105 times 10 to the 3, because we've gone from kilometers per second to meters per second, so we get 2 times 10 to 17 seconds. The next question says, at the beginning of the 20th century, astronomers identified that a number of galaxies were moving away from the Earth. State how astronomers knew that the galaxies were moving away from the Earth, and then Hubble suggested that the recession velocity of the galaxy was related to the distance of the galaxy from the Earth by the expression v equals h times by d. The graph shows some of Hubble's data. Assess the validity of the Hubble expression based on the data shown. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, it's the idea that the light or the radiation received from galaxies is redshifted, so the wavelength of light was longer than we expected. Now, in this second graph, it's looking at the information. Now, a straight line through the origin would be consistent with Hubble's expression because it's a directly proportional relationship, but there are outliers and they're far from the line, and only some of the points are close to the line, so the expression may not be valid. Or you could say the gradient is equal to the Hubble constant. There is scatter about the line, so therefore the value of Hubble's constant is uncertain, so it's another reason to suggest the expression may not be valid. The next question says, NGC 4889 is a galaxy which contains one of the biggest black holes ever discovered. State what is meant by a black hole. Then the mass of a black hole in NGC 4889 is believed to be 2.1 times 10 to the 10 times greater than that of the Sun. Calculate the radius of this event horizon. And then NGC 4889 is 3.1 times 10 to the 8 light years from the Earth and is receding at a velocity of 6.5 times 10 to the 6 meters per second. Estimate, using these data, an age in the seconds for the universe. So pause the video now, then unpause the video when you want to go through your answer. Right, learn the definition of a black hole. It's an object with an escape velocity greater than that of the speed of light. The next one, we're using the Schwarzschild radius of r equals 2gm over c squared. Remember to convert your mass from solar masses into kilograms by multiplying by that value of the mass of the Sun, 1.99 times 10 to the 30. Pop in the values and we get 6.2 times 10 to the 13 meters. In this next question, we know V equals hd, but V needs to be in kilometers per second, so we convert meters per second to kilometers per second. Distance needs to be in megaparsecs, so we convert our value given into megaparsecs by dividing by 3.26 times 10 to the 6, so it's 95. So therefore h is V over d, and it's 68. The age of the universe is 1 over 68, but that's not an appropriate unit. So we then use our conversion factor, and we work it through as shown on the screen to be 4.6 times 10 to the 17 seconds. The next question says, in 1999, a Type 1a supernovae was observed to be which contributed to the controversial conclusion that the expansion of the universe is accelerating. Explain why observations of the supernova led to the conclusion that the universe is expanding at an accelerating rate, and discuss why this conclusion is controversial. So pause the video now, then unpause the video when you want to go through your answer. Right, so the absolute magnitude of supernovae is known, which allows us to use supernovae as standard candles. Now, if we use the inverse square law, or the equation m minus m equals 5 log d over 10, this allows the distance to be calculated. Now, supernovae are very, very bright, so it can be seen in very distant galaxies from very far away. And it's taken billions of years from the light from the most distant galaxies to reach the Earth, so therefore these supernovae must have been produced a long time ago when the universe was very young. Now, measurements of redshift, so you can measure velocity, and the use of Hubble's law shows that actually the supernovae are fainter than expected, so it shows that they've been redshifted more than we thought. So this indicates to us that the universe is expanding now faster than when the supernovae first exploded, as the light has had to travel further to reach us than will be expected than if there was a constant rate of expansion, indicating that the universe is increasing in its expansion rate. So that brings an end to our revision session today. If you've been successful and you've learned in today's revision session, you'll be able to answer A-Level Physics examination style questions. You can assess your understanding in A-Level Physics and understand what topics you need to improve upon for A-Level Physics. So thank you so much for watching this revision session on AQA A-Level Physics Paper 3 on the Astrophysics option on the topic of cosmology. Thank you very much and have a lovely day.